What makes super-Earth so common in the galaxy, yet absent from our own solar system? Could these massive worlds, so different from Earth, still nurture life? How do their exotic atmospheres and interiors reshape our idea of habitability? In the vast expanse of our universe, where countless worlds orbit distant stars, there exists a class of planets that have captured the imagination of astronomers and dreamers alike. These celestial bodies, known as super-Earths, represent a fascinating category of exoplanets that challenge our understanding of planetary formation and the potential for life beyond our solar system. To truly appreciate the significance of these mysterious worlds, we must first explore what defines them and how they differ from the planet we call home. Super-Earths are not merely larger versions of our own world, but complex entities with unique characteristics that set them apart in the cosmic landscape. The term super-Earth might conjure images of a planet similar to ours, but grander in scale. Yet the scientific definition is more precise and perhaps more intriguing than one might initially imagine. In astronomical terms, a super-Earth is classified as an exoplanet with a mass greater than Earth's, but substantially less than that of ice giants like Neptune and Uranus. Typically, these worlds have masses ranging from about 1.5 to 10 times that of our planet, placing them in a category that doesn't exist within our own solar system. This absence from our cosmic neighborhood makes super-Earths particularly fascinating, as they represent planetary configurations that we cannot study directly in our own celestial backyard. What truly distinguishes super-Earths is not merely their size, but the potential diversity of their compositions and structures, which may differ dramatically from what we observe in our solar system. While some super-Earths might indeed be rocky worlds with thicker atmospheres than Earth, others could be ocean planets covered entirely in deep global oceans, hundreds of kilometers deep. There are even theoretical models suggesting that certain super-Earths might be composed primarily of carbon, with conditions extreme enough to form diamond layers deep within their interiors. This remarkable diversity in potential compositions makes the study of super-Earths a field rich with possibility and scientific discovery, challenging our preconceptions about what planets can be. The discovery of super-Earths has fundamentally altered our understanding of planetary systems and their formation, revealing that the architecture of our own solar system is but one of many possibilities in the universe. Prior to the detection of exoplanets, astronomers had only our solar system as a reference point, leading to models of planetary formation that suggested a clear division between small, rocky terrestrial worlds and large, gaseous giants. The emergence of super-Earths as a common category of exoplanets has forced scientists to revise these models, acknowledging that nature produces a much wider variety of planetary types than previously imagined. This realization has profound implications, not only for planetary science, but also for our search for habitable environments beyond Earth. One of the most intriguing aspects of super-Earths is their potential to maintain conditions suitable for life, despite their significant differences from our own planet. The gravitational forces on these worlds would be substantially stronger than what we experience on Earth, potentially leading to geological processes and atmospheric conditions that differ markedly from those we know. Yet, theoretical models suggest that many super-Earths could reside within the habitable zone of their host stars, where temperatures might allow for the existence of liquid water on their surfaces. This possibility raises fascinating questions about the adaptability of life and the various forms it might take in environments vastly different from our own. The methods used to detect and study super-Earths are as remarkable as the planets themselves, relying on ingenious techniques that allow astronomers to infer the presence of worlds too distant to observe directly. The transit method, which involves measuring the slight dimming of a star's light as a planet passes in front of it, has been particularly successful in identifying these elusive worlds. By carefully analyzing these minute changes in stellar brightness, scientists can determine not only the presence of a planet, but also its size and orbital period. Complementary techniques, such as radial velocity measurements, provide additional data about the planet's mass, allowing researchers to calculate its density and make inferences about its composition. As our detection methods have improved, the population of known super-Earths has grown dramatically, revealing that these worlds are not rare oddities, but rather common features in the galaxy. Recent surveys suggest that super-Earths may be among the most prevalent types of planets in the Milky Way, potentially outnumbering stars in our cosmic neighborhood. This abundance has led scientists to speculate about the processes that might contribute to the formation of so many intermediate-sized planets, and why our own solar system lacks examples of this planetary category. The answers to these questions may lie in the complex interplay of factors that influence planetary formation, from the composition of the protoplanetary disk to the dynamical interactions between developing worlds. The study of super-Earths has also prompted astronomers to reconsider the very definition of what constitutes a potentially habitable world, expanding our criteria beyond Earth-like conditions. While the search for life has traditionally focused on planets similar in size and composition to our own, the prevalence of super-Earths suggests that we should broaden our perspective. These larger worlds might offer different pathways to habitability, with stronger gravitational fields, potentially helping to retain atmospheres and geological processes that could maintain stable conditions over billions of years. This evolving understanding of habitability represents a paradigm shift in astrobiology, acknowledging that life might arise and persist in environments vastly different from those we find on Earth. The atmospheres of super-Earths present another frontier of scientific inquiry, with potentially complex compositions that could tell us much about their formation and evolution. A planet's atmosphere acts as both a shield against harmful radiation and a regulator of surface temperature, making it a critical factor in determining potential habitability. Theoretical models suggest that super-Earth atmospheres could range from thin, Earth-like envelopes to incredibly thick, Venus-like blankets that create extreme greenhouse effects. Some might even contain hydrogen and helium, the lightest elements, which would escape from smaller planets, but could be retained by the stronger gravity of super-Earths, creating atmospheric conditions unlike anything in our solar system. The internal structure of super-Earths remains a subject of intense scientific debate, with researchers developing sophisticated models to predict what might lie beneath their surfaces. Unlike Earth, with its clearly defined layers of crust, mantle, and core, super-Earths might exhibit entirely different internal architectures due to their greater mass and the resulting higher pressures. Some models suggest the possibility of exotic states of matter in the deep interiors of these worlds, where minerals might form structures not found naturally on Earth. These extreme conditions could give rise to geological processes and magnetic field generation that differ significantly from what we observe in our own planet, potentially affecting surface conditions in ways we are only beginning to understand. As we continue to explore the mysteries of super-Earths, each new discovery adds another piece to the puzzle of planetary formation and evolution, challenging our assumptions and expanding our cosmic perspective. The study of these worlds represents a convergence of multiple scientific disciplines, from astronomy and physics to geology and biology, each contributing unique insights into the nature of these enigmatic planets. With the launch of next-generation space telescopes and the development of increasingly sophisticated observational techniques, we stand on the brink of a new era in exoplanet research, one that promises to reveal even more about the diverse worlds that populate our galaxy. The journey to understand super-Earths is not merely a scientific endeavor, but a profound exploration of our place in the cosmos and the infinite possibilities that exist beyond the boundaries of our own solar system. In the vast cosmic nurseries where stars are born, the formation of planets begins with the gentle collapse of giant molecular clouds, creating swirling disks of gas and dust around young stellar embryos. Within these protoplanetary disks, countless tiny particles begin a journey of aggregation, gradually building up through collisions and gravitational attraction to form larger bodies that will eventually become planets. The birth of super-Earths follows this same fundamental process, yet under conditions that lead to worlds significantly more massive than our own planet. Understanding how these larger worlds come into existence requires us to explore the intricate dance of physics and chemistry that unfolds over millions of years in these stellar cradles. The initial stages of planetary formation begin with dust particles within the protoplanetary disk, sticking together through electrostatic forces, forming fluffy aggregates that gradually grow in size. As these aggregates continue to collide and merge, they develop sufficient gravitational attraction to pull in more material, accelerating their growth into larger bodies known as planetesimals. This process occurs throughout the disk, with materials closer to the young star consisting primarily of refractory elements like rock and metal, while those farther out contain more volatile compounds, including water ice and gases. The distribution of materials within the disk plays a crucial role in determining the final composition and characteristics of the planets that will eventually form. As planetesimals continue to grow through accretion, they enter a phase of runaway growth, where larger bodies grow at the expense of smaller ones, eventually forming planetary embryos with masses comparable to that of Earth's moon, or even larger. These embryos continue to collide and merge, their orbits sometimes crossing in a chaotic dance that leads to the formation of larger protoplanets. In regions where the protoplanetary disk is particularly massive or long-lived, this process can continue for longer periods, allowing protoplanets to accumulate more material and grow into the super-Earths we observe around other stars. The duration and intensity of this accretion phase are critical factors in determining whether a planet will remain Earth-sized or grow into a super-Earth. One of the key factors influencing the formation of super-Earths is the mass and composition of the protoplanetary disk itself, as more massive disks provide greater amounts of material for planetary embryos to accrete. Observations of young stellar systems have revealed that protoplanetary disks can vary significantly in mass, with some containing several times the material found in the disk that formed our own solar system. Systems with more massive disks are more likely to produce super-Earths, as the abundant material allows planetary embryos to grow larger before the disk dissipates. Additionally, the metallicity of the disk, the abundance of elements heavier than hydrogen and helium, plays a crucial role in determining how efficiently solid material can accrete into larger bodies. The location within the protoplanetary disk, where a planet forms, also significantly influences its final size and composition, with temperature gradients creating distinct regions where different types of materials can condense. Close to the young star, temperatures are too high for volatile compounds like water to condense into solid ice, limiting the available material for planet formation to primarily rock and metal. Farther out, beyond what astronomers call the snow line, temperatures drop sufficiently for water ice to form, dramatically increasing the amount of solid material available for planet formation. Planets forming in these outer regions can therefore grow more massive, potentially becoming super-Earths if sufficient material is available, and if migration processes bring them closer to their host star. Migration plays a fascinating and complex role in the formation of super-Earths, as gravitational interactions between forming planets and the surrounding protoplanetary disk can cause worlds to drift inward or outward from their birth locations. As a planet grows in mass, its gravitational influence on the disk becomes more significant, creating spiral waves that can exchange angular momentum between the planet and the disk material. This exchange of momentum can cause the planet to migrate inward toward the star, potentially bringing a world that formed beyond the snowline into the inner regions of the planetary system. Such migration processes may explain why we observe so many super-Earths in close orbits around their host stars, regions where they could not have formed in place due to the limited availability of solid material. The timing of planetary formation relative to the dissipation of the protoplanetary disk represents another critical factor in determining whether a planet will become a super-Earth or remain smaller. Protoplanetary disks have finite lifetimes, typically lasting only a few million years before radiation from the central star and other processes cause the gas and dust to dissipate. Planets that form early in this timeline have more time to accrete material and grow larger before the disk disappears, while those forming later may find their growth truncated by the diminishing availability of material. This temporal aspect of planetary formation creates a sort of cosmic race, with planetary embryos competing to grow as large as possible before the building blocks of planets are swept away by stellar winds and radiation. The formation of planetary cores represents a crucial stage in the development of super-Earths, as these cores must reach a critical mass before they can efficiently accrete and retain surrounding material. When a planetary core reaches approximately 10 Earth masses, its gravitational pull becomes strong enough to capture and hold on to hydrogen and helium gas from the surrounding protoplanetary disk. This process can lead to the formation of gas giants like Jupiter and Saturn if sufficient gas is available and if the core forms early enough in the disk's lifetime. However, if the disk gas dissipates before the core can accumulate a massive gaseous envelope, or if the core forms in a region with limited gas availability, the result may be a super-Earth with a substantial rocky or icy composition, but only a thin atmosphere compared to gas giants. The collisional history of forming planets also plays a significant role in determining their final characteristics, as giant impacts between planetary embryos can dramatically alter the mass, composition, and structure of these worlds. Computer simulations of planetary formation have shown that the final stages of planet assembly often involve several catastrophic collisions between similarly sized bodies, events that can strip away atmospheres, melt entire planetary surfaces, and even create entirely new worlds from the debris. These violent encounters may be particularly important in the formation of super-Earths, as they allow for the rapid assembly of larger bodies through the merger of smaller protoplanets. The aftermath of such collisions can also influence the subsequent evolution of these worlds, affecting their rotation rates, internal structure, and potential for hosting life. The role of magnetic fields in planetary formation represents an intriguing area of research that may have important implications for the development of super-Earths. As planetary cores form and begin to differentiate, with heavier materials sinking toward the center and lighter materials rising toward the surface, the motion of electrically conductive materials can generate magnetic fields. These magnetic fields may interact with the surrounding protoplanetary disk, potentially influencing accretion processes and protecting forming planets from harmful stellar radiation. For super-Earths, with their larger cores and potentially more vigorous internal dynamics, these magnetic effects may be particularly significant, contributing to the retention of atmospheres and the creation of conditions suitable for the emergence of life. The composition of the star around which planets form can provide important clues about the types of worlds likely to develop in that system. as stars with higher metallicity tend to host more massive planets. Astronomers have observed a correlation between the metal content of stars and the likelihood of finding gas giant planets orbiting them, suggesting that the availability of heavier elements is crucial for the formation of larger planetary cores. This relationship appears to extend to super-Earths as well, with systems containing these intermediate-sized planets more commonly found around stars with higher metallicity. This observation supports the core accretion model of planet formation, which posits that the formation of larger planets requires sufficient solid material to create massive cores before gas accretion can begin. The formation of multiple planetary systems introduces additional complexity to the process of super-Earth formation, as gravitational interactions between developing planets can influence their growth and evolution. In systems with multiple planetary embryos, orbital resonances can develop, with planets periodically aligning in ways that enhance their gravitational influence on each other. These resonant interactions can lead to orbital migration, increased collision rates, and the clearing of orbital zones, all of which affect the final architecture of the planetary system. Many of the super-Earth systems discovered by the Kepler mission and other surveys exhibit these resonant relationships, suggesting that gravitational interactions between forming planets play a crucial role in shaping these systems. The diversity of super-Earths discovered in recent years suggests that multiple formation pathways may lead to these intermediate-sized worlds, with different processes dominating under varying conditions. Some super-Earths may form primarily through the accretion of rocky material close to their host stars, while others might originate as icy bodies that form beyond the snowline and migrate inward, potentially losing some of their volatile components in the process. Still others might result from the collision of larger protoplanets that strip away much of their gaseous envelopes, leaving behind dense, rocky cores with thin atmospheres. This diversity in formation scenarios contributes to the wide range of densities, compositions, and structures observed among known super-Earths. The timescales involved in super-Earth formation span millions of years, representing a cosmic journey that unfolds over periods difficult for human minds to fully comprehend. From the initial collapse of a molecular cloud to the dissipation of the protoplanetary disk, the process of planet formation occurs gradually, with each stage building upon the previous one in a sequence of events that must unfold with precise timing. The formation of a super-Earth typically requires between 1 and 10 million years, depending on the mass of the protoplanetary disk, the location of the forming planet, and the specific formation pathway it follows. These extended timescales highlight the patience required of astronomers who study these processes, often inferring the details of planetary formation from snapshots of systems at various stages of development. The study of planetary formation has been revolutionized by advances in computational modeling, allowing scientists to simulate the complex physical processes that lead to the birth of planets like super-Earths. These sophisticated models incorporate numerous factors, including gravitational interactions, hydrodynamics, thermodynamics, and chemical processes, creating detailed simulations of how planetary systems evolve over time. By comparing the results of these simulations with observations of actual planetary systems, astronomers can test and refine their theories about how super-Earths form. This iterative process between theoretical modeling and observational discovery continues to improve our understanding of planetary formation, revealing the intricate processes that shape the diverse worlds we observe throughout the galaxy. The formation of super-Earths represents a delicate balance between competing processes, with factors that promote growth counteracted by those that limit it. On one hand, more massive protoplanetary disks, higher metallicity, and longer disk lifetimes all favor the formation of larger planets. On the other hand, gravitational interactions between forming planets, photoevaporation of disk material by stellar radiation, and the limited availability of solid material in certain regions can constrain planetary growth. The specific conditions in any given planetary system determine which of these factors dominate, leading to the remarkable diversity of planetary architectures we observe. This balance between growth and limitation helps explain why super-Earths are common in some systems while absent in others, and why our own solar system lacks these intermediate-sized worlds. As we continue to explore the mysteries of planetary formation, each new discovery adds another piece to the puzzle of how super-Earths come into existence, challenging our assumptions and expanding our understanding of planetary systems. The study of these worlds has revealed that the processes that shape planets are more complex and varied than previously imagined, with multiple pathways leading to similar outcomes. With the development of increasingly powerful telescopes and observational techniques, we are beginning to glimpse the earliest stages of planetary formation in young stellar systems, providing direct evidence of the processes that create super-Earths and other types of planets. These observations, combined with refined theoretical models, promise to deepen our understanding of the cosmic processes that have shaped not only the super-Earths we observe around distant stars, but also our own planet and its place in the universe. The journey into understanding what lies beneath the surfaces of super-Earths reveals a fascinating diversity of possible compositions, challenging our Earth-centric view of planetary structure. These intermediate-sized worlds, with masses ranging from 1 to 10 times that of our planet, may harbour interiors that differ dramatically from the layered structure we know on Earth. The immense pressures within these worlds can create exotic states of matter and unique mineral formations that do not naturally occur on our planet. By studying the density and composition of these distant worlds, scientists can piece together a picture of their internal architecture and the processes that shape them. Determining the composition of a super-Earth begins with measuring two fundamental properties: its mass and its radius. These measurements allow astronomers to calculate the planet's bulk density, which provides crucial clues about what the world might be made of. A planet with a high density, similar to Earth's, suggests a composition dominated by rock and metal, while a lower density indicates the presence of lighter elements such as water, gases, or other volatiles. This method of characterization, though seemingly straightforward, becomes increasingly complex as we consider the myriad ways materials might be distributed within a planetary body under extreme conditions. The internal structure of super-Earths likely consists of multiple layers, similar to Earth's core, mantle, and crust, but with proportions and properties that differ due to their greater mass. The core of a super-Earth might be significantly larger relative to its overall size, composed primarily of iron and nickel, just like Earth's core, but potentially under pressures so extreme that the iron exists in exotic crystalline forms. Surrounding this core would be a silicate mantle, possibly extending to greater depths than on Earth, where pressures and temperatures could create mineral assemblages unlike any found in our planet's interior. The outermost layer, the crust, might be thinner or thicker depending on the planet's thermal evolution and geological activity, influencing everything from surface features to atmospheric retention. One of the most intriguing possibilities for super-Earth composition is the existence of planets with a significant proportion of water, potentially forming global oceans hundreds of kilometers deep. These so-called water worlds would have a structure fundamentally different from Earth's, with a layer of high-pressure ice covering a rocky core and a vast liquid ocean above. The extreme pressures at the bottom of such oceans would create forms of ice that are denser than liquid water, preventing the ocean from contacting the rocky mantle directly. This arrangement could have profound implications for the cycling of elements and the potential for life, creating an environment where chemistry and biology might follow pathways quite different from those on Earth. The mineralogy of super-Earths presents another frontier of scientific inquiry, as the extreme pressures within these worlds can transform familiar elements into exotic materials not found on Earth. At pressures exceeding those in Earth's core, magnesium silicate minerals might transform into denser phases with different crystal structures, potentially altering the thermal and chemical evolution of the planet. Some theoretical models suggest that certain super-Earths might contain vast reservoirs of carbon, which under extreme pressure could form diamond layers deep within their interiors. These exotic compositions would not only affect the planet's internal dynamics, but could also influence its magnetic field generation, surface geology, and potential for harboring life. The atmospheres of super-Earths represent yet another component of their composition that can vary dramatically from world to world, influenced by factors such as the planet's mass, temperature, and formation history. A more massive super-Earth would have stronger surface gravity, enabling it to retain a thicker atmosphere that might extend to greater heights than Earth's atmosphere. The composition of these atmospheres could range from Earth-like mixtures of nitrogen and oxygen to hydrogen-dominated envelopes similar to gas giants, depending on the planet's distance from its star and the processes that shaped its evolution. These atmospheric differences would have profound effects on surface conditions, creating environments that might be familiar or utterly alien compared to our own world. The relationship between a super-Earth's composition and its potential habitability forms a central question in the study of these enigmatic worlds. A rocky super-Earth with a thin atmosphere might have surface conditions similar to Earth's, with temperatures allowing for liquid water and a climate suitable for life as we know it. Conversely, a water world with a thick hydrogen atmosphere might experience extreme greenhouse effects, rendering its surface too hot for life, despite being in the habitable zone. The interplay between composition, atmosphere, and orbital parameters creates a complex tapestry of possible environments, each with its own unique set of challenges and opportunities for the emergence and persistence of life. The study of super-Earth composition has been revolutionized by advances in theoretical modeling and computational simulations, allowing scientists to explore the behavior of materials under conditions impossible to replicate in laboratories on Earth. These models incorporate our understanding of high-pressure physics, thermodynamics, and mineralogy to predict how different materials might behave within the interiors of these massive worlds. By comparing the results of these simulations with observational data on planetary masses and radii, researchers can constrain the possible compositions of known super-Earths and make predictions about worlds yet to be discovered. This synergy between theoretical modeling and observational astronomy continues to deepen our understanding of planetary diversity in the cosmos. The diversity of observed densities among known super-Earths suggests a wide range of possible compositions, from predominantly rocky worlds to those with significant proportions of water or gas. Some super-Earths have densities similar to Earth's, indicating a composition dominated by rock and metal, while others have much lower densities, suggesting the presence of substantial volatile components. This variation in density cannot be explained by mass alone, as both smaller and larger super-Earths exhibit a range of densities that point to differences in composition rather than simply size. Understanding the factors that lead to this diversity in composition remains one of the key challenges in planetary science, with implications for our understanding of planet formation and evolution. The role of planetary formation in determining super-Earth composition cannot be overstated, as the conditions and materials present during a planet's birth fundamentally shape its final structure. Planets forming close to their host star might be primarily composed of refractory materials like rock and metal, while those forming farther out could incorporate more volatile compounds, including water ice and gases. Migration processes can further complicate this picture, potentially moving planets from their birth locations to regions with different environmental conditions, altering their compositions through atmospheric loss or gain. The complex interplay between formation location, migration history, and subsequent evolution creates the rich diversity of super-Earth compositions we observe today. The internal heat budget of super-Earths represents another crucial factor influencing their composition and structure. As the distribution and flow of heat within a planet affect everything from geological activity to magnetic field generation, larger planets generally retain more heat from their formation and generate more through radioactive decay, potentially leading to more vigorous mantle convection and geological activity than on smaller worlds. This enhanced internal heat could drive more extensive volcanism, plate tectonics, or other geological processes that cycle elements between the interior and surface, influencing atmospheric composition and long-term climate stability. The thermal evolution of a super-Earth thus plays a central role in determining its current state and potential for habitability. The possibility of differentiated interiors in super-Earths with distinct layers of varying composition adds another layer of complexity to our understanding of these. The vast tapestry of super-Earths, revealed through our observations, presents a remarkable diversity that challenges our understanding of planetary classification and evolution. These intermediate-sized worlds, though grouped under a single category, exhibit an astonishing range of characteristics that reflect the varied conditions under which they formed and evolved. From rocky landscapes to global oceans, from thin atmospheres to thick gaseous envelopes, super-Earths demonstrate that nature produces planets in configurations we never anticipated. This diversity not only enriches our knowledge of planetary science, but also expands our conception of where and how life might exist beyond Earth. Among the most intriguing types of super-Earths are those that appear to be predominantly rocky, with compositions similar to Earth's, but scaled up in size and mass. These rocky super-Earths likely formed in the inner regions of their planetary systems, where temperatures were too high for volatile compounds to condense into solid ice, limiting the available material to primarily rock and metal. Their higher densities suggest iron-nickel cores surrounded by silicate mantles, though the proportions of these components may differ significantly from Earth's due to their greater mass. The surfaces of these worlds might feature mountain ranges, valleys, and volcanic formations that dwarf their terrestrial counterparts, shaped by geological processes operating under stronger gravitational fields. In contrast to these rocky worlds, another category of super-Earths appears to contain substantial proportions of water, potentially forming global oceans that could be hundreds of kilometers deep. These water worlds represent a fascinating alternative to terrestrial planets like Earth, with their entire surfaces potentially covered by liquid water or high-pressure ice depending on their temperature profiles. The immense pressures at the bottom of such oceans would create exotic forms of ice that are denser than liquid water, preventing direct contact between the ocean and any rocky core that might exist beneath. These aquatic environments might host entirely different ecosystems from those we know on Earth, with life potentially evolving in the absence of continents and under perpetual twilight conditions if their atmospheres are thick enough to scatter sunlight effectively. A third category of super-Earths consists of what astronomers sometimes call gas dwarfs or mini-Neptunes, worlds that have accumulated significant gaseous envelopes around their rocky or icy cores. These planets occupy a middle ground between terrestrial worlds like Earth and gas giants like Neptune, with atmospheres that might extend to great heights due to their lower surface gravity compared to true gas giants. The composition of these atmospheres could range from hydrogen and helium to more complex mixtures, including water vapor, methane, and ammonia, depending on the planet's distance from its host star and its formation history. These gaseous envelopes would create surface conditions dramatically different from those on rocky planets, potentially rendering their surfaces uninhabitable by Earth-like life, despite their location within the habitable zone. Carbon-rich super-Earths represent yet another fascinating possibility. Worlds where carbon might be as abundant as oxygen is on Earth, potentially leading to exotic surface and interior compositions. Under the extreme pressures found within these planets, carbon could form diamond layers deep within their interiors, while surfaces might be covered in graphite or other carbon compounds rather than silicate rocks. The atmospheres of these worlds might contain significant amounts of carbon monoxide or methane, creating greenhouse effects that could maintain surface temperatures suitable for liquid water despite greater distances from their host stars. The potential existence of such carbon planets challenges our Earth-centric view of planetary composition and suggests that the building blocks of planets can vary dramatically from one system to another. The diversity of super-Earths extends to their orbital characteristics as well, with these worlds found in a wide range of distances from their host stars and in various orbital configurations. Some super-Earths orbit remarkably close to their stars, completing a revolution in just days or even hours, while others follow more distant orbits that take years to complete. Many have been discovered in multi-planet systems, where gravitational interactions between neighboring worlds create complex orbital resonances that influence their long-term stability and evolution. This variety in orbital arrangements suggests that super-Earths can form and persist under a wide range of dynamical conditions, further contributing to the diversity of these enigmatic worlds. The host stars around which super-Earths orbit add another dimension to their diversity, as these planets have been found around stars of various sizes, ages, and compositions, while many super-Earths have been detected around Sun-like stars similar to our own. They are particularly common around smaller M-dwarf stars, which are the most numerous type of star in our galaxy. These smaller, cooler stars present different environmental conditions for their planets, including increased stellar activity and tidal forces that can lead to synchronous rotation, with one side permanently facing the star. The prevalence of super-Earths around such diverse stellar types suggests that the formation of intermediate-sized planets is a robust process that can occur under a wide range of stellar conditions. The atmospheric diversity observed among super-Earths represents perhaps the most intriguing aspect of their variation, as these gaseous envelopes play crucial roles in determining surface conditions and potential habitability. Some super-Earths appear to have thin atmospheres similar to Earth's, composed primarily of nitrogen and oxygen, with trace amounts of other gases, while others might have thick hydrogen-dominated envelopes that create extreme greenhouse effects. The composition of these atmospheres depends on numerous factors, including the planet's mass, temperature, geological activity, and the intensity of radiation from its host star. Understanding this atmospheric diversity is essential for assessing the potential habitability of these worlds and for identifying possible biosignatures that might indicate the presence of life. The surface environments of super-Earths likely vary as dramatically as their compositions and atmospheres, creating a spectrum of possible conditions that might exist on these worlds. Rocky super-Earths might feature landscapes shaped by volcanism, tectonics, and erosion under stronger gravitational fields than we experience on Earth. Water worlds might have global oceans with depths far exceeding those of Earth's deepest trenches, potentially hiding any solid surface beneath hundreds of kilometers of water. The surfaces of gas dwarfs might be entirely obscured by thick cloud layers, with no solid surface accessible at all. This diversity of surface environments suggests that super-Earths could host conditions ranging from relatively Earth-like to utterly alien compared to anything in our solar system. The geological activity of super-Earths represents another area where significant diversity might exist, influenced by factors such as planetary mass, composition, and internal heat budget. Larger super-Earths might experience more vigorous mantle convection and plate tectonics than Earth, leading to more frequent volcanic activity and mountain building. Some might lack plate tectonics entirely, instead experiencing a different mode of surface renewal through volcanic processes or mantle overturn. The geological evolution of these worlds would be profoundly affected by their stronger gravitational fields, which could influence the height of mountains, the depth of valleys, and the overall topography of their surfaces. This geological diversity would in turn affect atmospheric composition, climate regulation, and the potential for habitability over geological timescales. The magnetic fields generated by super-Earths add another layer to their diversity, as these protective shields against stellar radiation depend on factors including core composition, rotation rate, and internal heat flow. Planets with larger iron-nickel cores and more rapid rotation might generate stronger magnetic fields than Earth's, offering enhanced protection to their surfaces and any potential life forms. Conversely, slowly rotating super-Earths, or those with less conductive cores, might have weaker magnetic fields, leaving their surfaces more exposed to stellar winds and cosmic radiation. This variation in magnetic protection could significantly influence atmospheric retention and surface conditions, affecting the potential for these worlds to host life as we know it. The age of super-Earths introduces yet another dimension to their diversity, as planets of different ages have had varying amounts of time to evolve and change. Young super-Earths might still be cooling from their formation, experiencing intense volcanic activity and outgassing that shapes their primordial atmospheres. Older worlds might have progressed through different evolutionary stages, potentially losing significant portions of their original atmospheres to space, or developing secondary atmospheres through geological processes. The age of a super-Earth relative to its host star's activity cycle also plays a crucial role in determining its current state, as stars tend to be more active in their youth, emitting higher levels of radiation that can affect planetary atmospheres and surfaces. The diversity of super-Earths challenges us to expand our thinking about planetary classification and the potential for life in the universe. Rather than fitting neatly into categories based on our solar system's architecture, these worlds demonstrate that planets can exist in configurations we never anticipated, with compositions, structures, and conditions that differ dramatically from what we find in our own cosmic neighborhood. This diversity suggests that the processes of planet formation and evolution are more complex and varied than previously imagined, creating a rich tapestry of worlds throughout the galaxy. As we continue to discover and characterize these enigmatic planets, each new addition to our catalogue further enriches our understanding of planetary science and the potential for life beyond Earth. As we turn our attention to the methods by which we detect these enigmatic worlds, we find ourselves drawn to one of the most elegant techniques in the astronomer's toolkit, the transit method. This approach to finding planets beyond our solar system relies on one of the most fundamental phenomena in the universe, the passage of one celestial body in front of another, creating a subtle shadow that can be detected across vast cosmic distances. The transit method has revolutionized our understanding of planetary systems, revealing thousands of worlds that would otherwise remain hidden from our view. It is through this technique that many of the super-Earths we now study were first brought to our attention. their presence inferred from the faint dimming of their host star's light. The principle behind the transit method is beautifully simple in concept, though its execution requires extraordinary precision and technological sophistication. When a planet passes directly between its host star and our line of sight, it blocks a small fraction of the star's light, causing a measurable decrease in brightness that lasts for the duration of the transit. This diminution of starlight is typically quite small, especially for Earth-sized or super-Earth planets, which may block only 1/100th of 1% or less of their star's total light. Detecting such minuscule changes requires instruments of remarkable sensitivity and the ability to monitor stars continuously over extended periods. The periodic nature of these dips in brightness, their regular recurrence at predictable intervals, provides confirmation that we are indeed observing the transit of an orbiting planet, rather than some random stellar fluctuation. The history of the transit method as a means of planet detection stretches back further than one might imagine, with theoretical discussions dating to the mid-20th century. Astronomers had long understood that planetary transits should occur in other planetary systems, just as Venus and Mercury occasionally transit across the face of our Sun from our perspective. However, the technological challenges involved in detecting these tiny signals from light years away seemed insurmountable for decades. It was not until 1999 that the first exoplanet transit was successfully observed, when the planet HD 209458b, previously discovered through the radial velocity method, was seen crossing in front of its host star. This breakthrough demonstrated that transits could indeed be detected and paved the way for the development of dedicated transit surveys that would follow in the coming years. The design and implementation of space-based transit surveys represented a quantum leap in our ability to detect and characterize super-Earths and other exoplanets. Unlike ground-based observatories, which must contend with the interference of Earth's atmosphere and the interruption of daylight, space telescopes can monitor stars continuously with unprecedented precision. The Kepler Space Telescope, launched by NASA in 2009, was the first mission specifically designed to search for Earth-sized planets using the transit method. Kepler stared at a single patch of sky containing over 150,000 stars for 4 years, detecting the minute dips in brightness that betray the presence of orbiting planets. This revolutionary approach yielded thousands of planet candidates, including numerous super-Earths that have fundamentally reshaped our understanding of planetary demographics in our galaxy. The process of analyzing transit data to identify potential planets is both an art and a science, requiring sophisticated algorithms and careful human scrutiny to distinguish true planetary signals from various sources of noise. When a star's light curve, the graph of its brightness over time, shows a periodic dip, astronomers must first rule out other phenomena that might mimic a transit, such as stellar variability, eclipsing binary stars, or instrumental artifacts. The shape of the transit curve provides important clues about the nature of the transiting object, with planets producing characteristically symmetric dips that begin and end gradually rather than abruptly. The depth of the transit reveals the size of the planet relative to its host star, while the duration provides information about the planet's orbital distance and the inclination of its orbit relative to our line of sight. The information we can extract from transit observations extends far beyond the mere detection of a planet's presence, offering insights into its physical characteristics and orbital parameters. By measuring the depth of the transit, the amount by which the star's light is dimmed, astronomers can calculate the planet's radius relative to its host star. When combined with independent measurements of the star's size, this allows determination of the planet's physical radius, a fundamental parameter that helps classify it as a super-Earth or another type of planet. The period of the transits, the time between successive events, directly reveals the planet's orbital period through Kepler's third law, which relates orbital period to distance from the host star. These basic measurements form the foundation upon which our understanding of these distant worlds is built. The transit method has proven particularly effective at detecting planets in close orbits around their host stars, including the hot super-Earths that have challenged our theories of planetary formation and evolution. These worlds, with orbital periods of just days or even hours, experience extreme conditions that would be utterly inhospitable to life as we know it. Yet they provide valuable insights into the diversity of planetary systems. The prevalence of such close-in super-Earths has prompted astronomers to reconsider models of planetary migration, suggesting that many planets may form farther from their stars and then migrate inward over time. The study of these extreme worlds has expanded our understanding of the possible architectures of planetary systems and the physical processes that shape them over cosmic timescales. One of the most powerful applications of the transit method is its ability to detect multiple planets in the same system, revealing the rich complexity of planetary architectures throughout the galaxy. When a system contains multiple transiting planets, their gravitational interactions can produce subtle variations in transit timing and duration that provide additional information about their masses and orbital characteristics. These transit timing variations have been instrumental in confirming the planetary nature of many candidates and in measuring the masses of planets that would otherwise be detectable only through their transits. The discovery of compact multi-planet systems containing multiple super-Earths has been one of the most surprising findings of transit surveys, challenging our preconceptions about how planetary systems form and evolve. The atmospheric characterization of super-Earths represents another frontier made accessible by the transit method through a technique known as transmission spectroscopy. When a planet transits its host star, a small fraction of the star's light passes through the planet's atmosphere before reaching our telescopes, with different wavelengths of light being absorbed by different atmospheric constituents. By carefully analyzing the spectrum of the starlight during a transit and comparing it to the spectrum outside of transit, astronomers can identify the fingerprints of specific molecules in the planet's atmosphere. This technique has been used to detect water vapor, methane, carbon dioxide, and other compounds in the atmospheres of some exoplanets, providing insights into their composition and potential habitability for super-Earths, which represent a particularly intriguing category of potentially habitable worlds. Such atmospheric characterization is a crucial step toward assessing their suitability for life. The technological evolution of transit detection continues apace, with new instruments and missions building upon the legacy of Kepler and expanding our ability to find and characterize super-Earths. The Transiting Exoplanet survey satellite, launched by NASA in 2018, is conducting an all-sky survey to detect transiting planets around the brightest and nearest stars in our galaxy, focusing on worlds that will be amenable to follow-up observations with other facilities. These brighter targets are particularly valuable for atmospheric characterization studies, as their greater apparent brightness allows for more detailed spectroscopic analysis. Future missions, including the James Webb Space Telescope and planned next-generation observatories, promise to further enhance our ability to study the atmospheres of super-Earths and search for potential biosignatures that might indicate the presence of life. The statistical analysis of transit survey data has revealed profound insights into the distribution and prevalence of super-Earths throughout our galaxy. By carefully accounting for the detection biases inherent in the transit method, which is more sensitive to larger planets in close orbits around smaller stars, Astronomers have estimated that such worlds are remarkably common, potentially outnumbering stars in the Milky Way. These findings suggest that our solar system, with its distinct lack of planets in the super-Earth size range, may be somewhat atypical compared to the galactic norm. The implications of this realization extend beyond planetary science, touching on questions about the potential prevalence of habitable environments and the possibility of life elsewhere in the universe. The refinement of transit detection techniques continues to push the boundaries of what is possible, with astronomers developing increasingly sophisticated methods to extract planetary signals from noisy data. Machine learning algorithms have been trained to recognize the subtle signatures of transiting planets, sometimes identifying signals that might have been missed by traditional analysis methods. These advances have been particularly valuable for identifying smaller planets with shallower transits, including Earth-sized and super-Earth worlds that produce only the most minute dips in stellar brightness. As these techniques continue to improve, our ability to detect and characterize ever smaller planets in longer period orbits will expand, gradually building a more complete picture of the planetary census in our galactic neighborhood. The international collaboration that underpins modern transit surveys represents another crucial aspect of their success, with scientists and institutions around the world contributing to the collective effort to find and understand distant worlds. Ground-based observatories play a vital role in confirming planet candidates identified by space missions and in conducting follow-up observations to refine our knowledge of these systems. The synergy between space-based transit surveys and ground-based follow-up observations has been essential to the success of exoplanet detection programs, creating a global network of researchers and facilities working together to explore the cosmos. This collaborative spirit has accelerated the pace of discovery and fostered a sense of shared wonder about the diverse worlds that populate our galaxy. As we reflect on the remarkable achievements of the transit method in revealing the population of super-Earths throughout our galaxy, we are reminded of the power of simple principles applied with extraordinary precision. The observation of tiny shadows cast by distant worlds has fundamentally transformed our understanding of planetary systems and our place in the cosmos. Each transit measurement, each light curve analyzed, contributes to a growing tapestry of knowledge about the diverse worlds that orbit stars beyond our own. The transit method has not only detected thousands of planets, but has also enabled us to begin characterizing their properties, atmospheres, and potential habitability, opening new frontiers in our quest to understand the universe and our place within it. Among the various methods astronomers employ to detect planets beyond our solar system, direct imaging stands as perhaps the most intuitively appealing approach, offering the possibility of actually seeing these distant worlds, rather than inferring their presence through indirect means. The concept is beautifully simple: to capture actual images of exoplanets, separating their faint light from the overwhelming glare of their host stars. Yet the execution of this concept represents one of the most formidable challenges in modern astronomy, requiring extraordinary technological innovation and precision to overcome the vast differences in brightness between stars and their planetary companions. The pursuit of direct imaging has driven the development of increasingly sophisticated instruments and techniques, gradually expanding our ability to observe these previously invisible worlds and gather information about their properties. The fundamental challenge of direct imaging stems from the extreme contrast between the brightness of a star and the faint light reflected by its orbiting planets. A star like our Sun outshines Jupiter by a factor of about 1 billion in visible light, creating a contrast ratio that makes detecting the planetary signal akin to spotting a firefly next to a searchlight from many miles away. This challenge is compounded by the small angular separation between stars and their planets, especially for worlds in Earth-like orbits, which appear extremely close to their host stars when viewed from interstellar distances. Overcoming these obstacles requires not only collecting large amounts of light to detect the faint planetary signal, but also employing sophisticated techniques to suppress the starlight that would otherwise overwhelm the much dimmer planetary light. The development of coronagraphs represents one of the most significant technological advances in the quest to directly image exoplanets, offering a means to artificially eclipse the light from a star and reveal the faint planets orbiting it. These devices, which can be thought of as masks placed inside a telescope to block starlight, work by carefully manipulating the wavefront of light to create a region of darkness around the star where planets might be visible. Modern coronagraphs employ complex designs that can achieve contrast ratios of billions to 1, enabling the detection of planets that are many orders of magnitude fainter than their host stars. The refinement of these instruments has been incremental but steady, with each generation of coronagraphs pushing the boundaries of what is possible in terms of starlight suppression and planetary detection. Another crucial innovation in direct imaging has been the development of adaptive optics systems, which correct for the distortions in starlight caused by Earth's atmosphere, allowing ground-based telescopes to achieve much sharper images than would otherwise be possible. These systems work by measuring the atmospheric distortion in real time, using a bright reference star or an artificial laser guide star, then adjusting a deformable mirror to compensate for these distortions, hundreds or even thousands of times per second. The implementation of adaptive optics has revolutionized ground-based astronomy, enabling telescopes to approach their theoretical resolution limits and significantly improving their ability to detect faint objects close to bright stars. This technology has been particularly valuable for direct imaging surveys, where the ability to achieve sharp, stable images is essential for separating planetary light from stellar glare. The combination of coronagraphy and adaptive optics has enabled ground-based telescopes to directly image several dozen exoplanets to date, including some in the super-Earth mass range, though most of these worlds are young, hot, and located relatively far from their host stars. These characteristics make them easier to detect than older, cooler planets in closer orbits, as young planets are still glowing with the heat of their formation, emitting strongly in the infrared, while their greater distance from their host stars reduces the contrast challenge. The first direct image of a multi-planet system was obtained in 2008, revealing 4 planets orbiting the star HR 8799, each with masses several times that of Jupiter. This remarkable achievement demonstrated that direct imaging was indeed possible and opened the door to further discoveries using this technique. Space-based observatories have also played a crucial role in advancing direct imaging capabilities, free from the distortions and limitations imposed by Earth's atmosphere. While no space telescope has yet been designed specifically for exoplanet imaging, instruments like the Hubble Space Telescope and the Spitzer Space Telescope have contributed to the field, with Hubble capturing the first visible light image of an exoplanet in 2008. The upcoming James Webb Space Telescope, with its large aperture and advanced instruments, promises to significantly enhance our ability to directly image exoplanets, including potentially some smaller, cooler worlds that have eluded detection thus far. These space-based platforms complement ground-based efforts, operating in wavelength ranges and under conditions that would be difficult or impossible to achieve from Earth's surface. The characterization of directly imaged exoplanets provides unique insights into their properties, including their temperatures, atmospheric compositions, and orbital characteristics. By analyzing the spectrum of light from these worlds, astronomers can identify specific molecules in their atmospheres, such as water vapor, methane, and carbon monoxide, offering clues about their formation and evolution. The colors and brightness variations of these planets can also reveal information about cloud structures, atmospheric dynamics, and surface features, though such details remain challenging to resolve for all but the most favorable targets. For super-Earths, which represent a particularly intriguing category of potentially habitable worlds, direct imaging could eventually provide the means to study their atmospheres in detail and search for possible biosignatures that might indicate the presence of life. The direct imaging of super-Earths presents even greater challenges than imaging larger gas giant planets, due to their smaller size, lower mass, and typically closer proximity to their host stars. These factors combine to make super-Earths significantly fainter and harder to separate from stellar glare than their more massive counterparts. To date, no true super-Earth has been directly imaged, as current technology remains insufficient to overcome the contrast and angular separation challenges for these smaller worlds. However, theoretical studies and technological developments suggest that direct imaging of super-Earths may become possible in the coming decades, with the next generation of ground-based extremely large telescopes and dedicated space-based missions designed specifically for exoplanet imaging. The concept of star shades represents an innovative approach to enhancing direct imaging capabilities, involving the use of a large, specially shaped occulting disk, flown in formation with a space telescope to block starlight before it ever enters the instrument. These star shades, which could be tens of meters in diameter, would be positioned tens of thousands of kilometers from the telescope, precisely aligned to cast a shadow on the telescope aperture and enable observations of faint planets close to their host stars. This approach offers several advantages over internal coronagraphs, including the potential for higher contrast ratios and the ability to observe planets at smaller angular separations from their stars. Several starshade concepts are currently under study by NASA and other space agencies, with the possibility of deployment in the coming decades as part of future exoplanet imaging missions. The development of extremely large ground-based telescopes with apertures of 25 meters or more promises to significantly advance direct imaging capabilities in the coming years. These next-generation facilities, including the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will collect much more light than current telescopes, enabling the detection of fainter objects at smaller angular separations from their host stars. When combined with advanced adaptive optics systems and sophisticated coronagraphs, these telescopes may be capable of directly imaging some of the larger and more distant super-Earths, particularly those around nearby stars. The increased light-gathering power of these facilities will also enable more detailed spectroscopic characterization of directly imaged planets, providing insights into their atmospheric compositions and potential habitability. The direct imaging method offers unique advantages over other detection techniques, particularly in its ability to study planets that are located far from their host stars and to provide information about their atmospheric compositions and properties. Unlike the transit and radial velocity methods, which are most sensitive to planets in close orbits, direct imaging can reveal planets in wider orbits that might otherwise remain undetected. This capability is particularly valuable for understanding the full architecture of planetary systems and the processes that shape their formation and evolution. Additionally, direct imaging allows astronomers to study the same planet repeatedly over time, monitoring changes in its atmosphere or brightness that might provide insights into its climate, weather patterns, or other dynamic processes. The challenges of direct imaging have inspired a remarkable spirit of innovation and collaboration among astronomers, engineers, and scientists from around the world. The development of new technologies and techniques for exoplanet imaging has required expertise in fields ranging from optics and adaptive optics to data processing and astronomical instrumentation. International teams have worked together to design, build, and operate increasingly sophisticated instruments, sharing knowledge and resources to advance the frontiers of what is possible. This collaborative approach has been essential to the progress made thus far in direct imaging, and will continue to be crucial as we push toward the goal of imaging smaller, potentially habitable worlds like super-Earths. The future of direct imaging holds exciting possibilities for the detection and characterization of Earth-like planets and potentially habitable super-Earths around nearby stars. Several concepts for future space missions specifically designed for exoplanet imaging are currently under study, including the Habitable Exoplanet Observatory, HabEx, and the Large UV Optical IR Surveyor, LUVOIR, which could potentially image dozens of potentially habitable worlds and analyze their atmospheres for signs of life. These missions would represent a quantum leap in our ability to directly image and characterize exoplanets, building upon the technological foundations established by current and upcoming facilities. The realization of such ambitious concepts would mark a transformative moment in humanity's quest to understand our place in the universe and search for life beyond Earth. The direct imaging of exoplanets, including the eventual goal of capturing images of potentially habitable super-Earths, represents one of the most compelling frontiers in modern astronomy. Each new image of a distant world offers not only scientific data, but also a profound connection to the vast diversity of planets that exist throughout our galaxy. The technical challenges involved in these observations are formidable, but the potential rewards, in terms of scientific understanding and the possibility of finding evidence of life beyond Earth, are equally immense. As we continue to develop and refine the technologies and techniques needed for direct imaging, we move closer to answering some of the most fundamental questions about our place in the cosmos and the prevalence of potentially habitable environments throughout the universe. As we stand at the threshold of a new era in exoplanet exploration, the horizon of discovery is illuminated by an array of emerging technologies that promise to transform our understanding of super-Earths and their potential for harboring life. These next-generation tools represent the culmination of decades of scientific innovation, engineering prowess, and international collaboration, each designed to overcome the limitations that have constrained our ability to study these distant worlds. The coming decades will witness the deployment of increasingly sophisticated instruments capable of detecting smaller planets, characterizing their atmospheres with unprecedented detail, and potentially identifying the chemical signatures of biological activity. This technological revolution in astronomical observation will gradually lift the veil that has obscured our view of these enigmatic worlds, revealing insights that may fundamentally reshape our understanding of planetary formation, evolution, and habitability throughout the cosmos. The James Webb Space Telescope, launched in late 2021, stands as the most powerful space observatory ever constructed, bringing transformative capabilities to the study of exoplanets, including super-Earths. With its 6.5-meter segmented mirror and suite of advanced instruments, Webb can detect the faint infrared light from distant worlds, enabling spectroscopic analysis of their atmospheres with unprecedented sensitivity. This capability allows astronomers to identify specific molecules such as water vapor, carbon dioxide, and methane in the atmospheres of transiting super-Earths, providing crucial information about their composition and potential habitability. Webb's ability to observe in the infrared is particularly valuable for studying cooler planets, including those in the habitable zones of their host stars, where temperatures might allow for the existence of liquid water on their surfaces. The telescope's contributions to exoplanet science have already begun to reshape our understanding of these worlds, with each new observation adding another piece to the puzzle of planetary diversity in our galaxy. Ground-based, extremely large telescopes currently under construction around the world represent another quantum leap in our ability to directly image and characterize exoplanets, including potentially some super-Earths. These mammoth observatories, with primary mirrors ranging from 25 to 39 meters in diameter, will collect vastly more light than current telescopes, enabling the detection of fainter objects at smaller angular separations from their host stars. The Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope each incorporate sophisticated adaptive optics systems and advanced coronagraphs designed to suppress starlight and reveal the faint planetary signals that have eluded detection thus far. These facilities will be particularly powerful when used in conjunction with spectroscopic instruments capable of analyzing the light from directly imaged planets, providing insights into their atmospheric compositions, temperatures, and other physical properties. The unprecedented resolution and light-gathering power of these telescopes may eventually allow us to directly image some of the larger super-Earths orbiting nearby stars, bringing these distant worlds into sharper focus than ever before. The development of advanced coronagraphy technology continues to push the boundaries of what is possible in terms of starlight suppression, with new designs promising contrast ratios sufficient to detect Earth-like planets around nearby stars. These next-generation coronagraphs employ innovative approaches such as vector vortex masks, phase-induced amplitude apodization, and hybrid designs that combine multiple starlight suppression techniques to achieve the extreme contrast ratios needed for planetary detection. Some of these advanced coronagraphs are being designed for integration with space telescopes, where the absence of atmospheric distortion allows them to operate at their theoretical performance limits. Others are being developed for ground-based extremely large telescopes, where they will work in conjunction with adaptive optics systems to correct for atmospheric turbulence and achieve the precise wavefront control needed for effective starlight suppression. The refinement of these technologies represents a critical step toward the direct imaging and characterization of potentially habitable super-Earths, bringing us closer to answering fundamental questions about the prevalence of life-bearing worlds throughout the cosmos. The concept of star shades, large occulting disks designed to fly in formation with space telescopes, offers a promising alternative approach to achieving the extreme contrast ratios needed for direct imaging of Earth-like exoplanets. These precisely engineered structures, which could span tens of meters in diameter, would be positioned tens of thousands of kilometers from a space telescope, precisely aligned to cast a shadow on the telescope's aperture and block starlight before it ever enters the instrument. This approach offers several advantages over internal coronagraphs, including the potential for higher contrast ratios and the ability to observe planets at smaller angular separations from their host stars. Several starshade concepts are currently under study by NASA and other space agencies, with detailed engineering analyses exploring the challenges of deployment, station keeping, and formation flying required for such missions. The successful implementation of a starshade mission would dramatically enhance our ability to directly image and characterize potentially habitable super-Earths, potentially enabling the detection of dozens of such worlds around nearby stars and the spectroscopic analysis of their atmospheres for signs of life. Space interferometry represents another frontier in exoplanet detection technology, using multiple telescopes working in concert to achieve the resolution and contrast needed to directly image Earth-like planets around nearby stars. This approach involves combining the light from multiple separated telescopes to create interference patterns that can be analyzed to reconstruct images of planetary systems with extraordinary detail. Space-based interferometers could potentially achieve angular resolutions far beyond what is possible with single telescopes, enabling the direct imaging of Earth-sized planets in the habitable zones of sun-like stars. Several concepts for space interferometers have been proposed, including missions that would use multiple spacecraft flying in precise formation to create a virtual telescope with an effective aperture equivalent to the distance between the individual telescopes. While significant technical challenges remain in developing the precise formation, flying, and beam combination technologies required for such missions, the potential scientific payoff is enormous, offering the possibility of not only detecting potentially habitable super-Earths, but also obtaining detailed images of their surfaces and atmospheres. The refinement of high-resolution spectroscopy techniques will be crucial for characterizing the atmospheres of super-Earths and searching for potential biosignatures that might indicate the presence of life. Next-generation spectrographs, both for ground-based extremely large telescopes and future space missions, will need to achieve unprecedented stability and sensitivity to detect the subtle spectral signatures of molecules in the atmospheres of these distant worlds. These instruments will employ advanced technologies such as laser frequency combs for precise wavelength calibration, ultra-stable optical benches to minimize instrumental drifts, and highly efficient detectors to maximize the collection of precious photons from faint planetary signals. The development of these spectroscopic capabilities represents a critical step toward the ultimate goal of identifying signs of biological activity in exoplanet atmospheres, such as the simultaneous presence of oxygen and methane in chemical disequilibrium, which could potentially indicate the presence of life as we know it. Each advancement in spectroscopic technology brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? The application of machine learning and artificial intelligence to exoplanet data analysis is transforming our ability to detect and characterize faint planetary signals in increasingly complex datasets. These advanced algorithms can identify subtle patterns in data that might escape human notice, distinguishing true planetary signals from various sources of noise and instrumental artifacts with greater reliability than traditional analysis methods. Machine learning techniques are particularly valuable for processing the enormous datasets generated by transit surveys and radial velocity monitoring programs, where the volume of data can overwhelm conventional analysis approaches. These algorithms can also optimize observational strategies in real time, helping astronomers make the most efficient use of valuable telescope time by focusing on the most promising targets and observational parameters. As these techniques continue to evolve, they will play an increasingly central role in exoplanet research, enhancing our ability to detect smaller planets, characterize their properties, and identify the most promising candidates for follow-up observations with next-generation instruments. The development of advanced space-based ultraviolet and optical telescopes designed specifically for exoplanet characterization represents another exciting frontier in the coming decades. Concepts such as the Habitable Exoplanet Observatory, HabEx, and the Large UV Optical IR Surveyor, LUVOIR, are being studied as potential flagship missions that could revolutionize our ability to directly image and characterize Earth-like planets around nearby stars. These observatories would incorporate large apertures, sophisticated starlight suppression systems, and advanced spectrographs capable of analyzing the atmospheres of directly imaged planets for potential biosignatures. The design of these missions involves careful consideration of numerous factors, including the trade-offs between mirror size, starlight suppression performance, wavelength coverage, and the overall complexity and cost of the mission. If realized, these observatories would represent a quantum leap in our ability to study potentially habitable super-Earths, potentially providing definitive evidence of biological activity beyond our solar system within the coming decades. The exploration of novel detection methods, beyond the established techniques of transit, radial velocity, and direct imaging, continues to expand the toolkit available for exoplanet discovery and characterization. Approaches such as microlensing, which takes advantage of the gravitational lensing effect to detect planets around distant stars, have already proven valuable for finding planets in wide orbits that would be difficult to detect by other means. Other emerging techniques include astrometry, which precisely measures the wobble of a star on the plane of the sky rather than along our line of sight, and pulsar timing, which uses the incredibly regular pulses from rapidly rotating neutron stars to detect the subtle gravitational influences of orbiting planets. Each of these methods has its own strengths and limitations, and the continued refinement of these techniques will contribute to a more comprehensive understanding of the diversity of planetary systems throughout our galaxy. The development of complementary detection approaches ensures that we can explore the full range of possible planetary architectures, including those that might be missed by any single method alone. The international collaboration that underpins the development of next-generation exoplanet detection technologies represents a crucial aspect of their potential success, bringing together resources, expertise, and perspectives from around the world. Major facilities, such as the James Webb Space Telescope and the upcoming extremely large telescopes, are the result of decades of cooperation between space agencies, research institutions, and industry partners across multiple continents. This collaborative approach not only pools financial resources, but also leverages the specialized knowledge and capabilities of different organizations, creating a synergistic effect that accelerates technological development and scientific discovery. The global nature of exoplanet research also fosters a sense of shared purpose and wonder about the cosmos, transcending national boundaries and cultural differences in the pursuit of fundamental knowledge about our place in the universe. This spirit of international cooperation will be essential for tackling the ambitious technological challenges involved in the direct imaging and characterization of potentially habitable super-Earths in the coming decades. The integration of multiple detection and characterization techniques will be increasingly important as we push toward the goal of studying potentially habitable super-Earths in detail, with each method providing complementary information about these distant worlds. The combination of transit observations with radial velocity measurements allows for the determination of both the radius and mass of a planet, enabling calculation of its density and providing insights into its composition. Direct imaging can then potentially reveal the planet's atmospheric properties through spectroscopic analysis, while astrometric measurements might provide additional constraints on the planet's mass and orbital characteristics. This multi-pronged approach to exoplanet characterization creates a more complete picture of these worlds than any single method could achieve alone, allowing astronomers to test and refine their understanding of planetary formation, evolution, and habitability. The continued development and integration of these diverse techniques will be essential for unraveling the mysteries of super-Earths and their potential for hosting life beyond our solar system. The philosophical and societal implications of next-generation exoplanet detection technologies extend far beyond their scientific value, touching on fundamental questions about humanity's place in the cosmos and our relationship with the wider universe. The potential discovery of evidence for life beyond Earth, particularly on a world as seemingly familiar as a super-Earth, would represent one of the most profound moments in human history, challenging our understanding of ourselves and our place in the cosmic order. These technological advances also inspire wonder and curiosity about the universe, fostering a sense of connection to the vast tapestry of worlds that populate our galaxy and beyond. The development of these instruments represents humanity's collective aspiration to explore and understand the cosmos, pushing the boundaries of what is possible through ingenuity, perseverance, and cooperation. As we continue to refine and deploy these next-generation tools for discovery, we carry forward a legacy of exploration that has defined our species since the first humans looked up at the night sky and wondered about the nature of the lights shining above them, bringing us closer to answering questions that have captivated human imagination for millennia. The concept of the habitable zone represents one of the most compelling frameworks in our search for life beyond Earth, defining the region around a star where conditions might be just right for liquid water to exist on a planet's surface. This delicate balance between too hot and too cold has been metaphorically described as the Goldilocks zone, where conditions are neither too extreme nor too mild, but rather perfectly suited for life as we know it. Within this cosmic sweet spot, a planet receives sufficient energy from its host star to maintain water in its liquid state, while avoiding the runaway greenhouse effects that would boil away oceans or the frigid temperatures that would freeze them solid. The boundaries of this zone are not fixed, but rather shift depending on numerous factors, including the star's size, temperature, and age, as well as the planet's atmospheric composition and geological activity. The inner edge of the habitable zone marks the boundary where a planet would experience a runaway greenhouse effect, similar to what we observe on Venus, where temperatures are high enough to vaporize any surface water. Beyond this point, the decreasing stellar flux allows for the possibility of liquid water, assuming appropriate atmospheric conditions exist to maintain surface pressures sufficient for water to remain stable. The outer edge of the habitable zone is defined by the distance at which even a dense carbon dioxide atmosphere would be unable to prevent water from freezing solid, limiting the greenhouse effect's ability to trap sufficient heat. Between these boundaries lies a region of possibility, where the interplay of stellar radiation, atmospheric composition, and planetary characteristics could create conditions suitable for the existence of liquid water and potentially life as we understand it. The characteristics of the host star play a crucial role in determining the location and extent of the habitable zone, with more massive, hotter stars having habitable zones located farther from their surfaces than smaller, cooler stars. For stars like our Sun, a G-type main sequence star, the habitable zone extends from roughly 0.95 to 1.37 astronomical units, placing Earth comfortably within this region, and explaining why our planet has maintained liquid water throughout most of its history. Smaller K-type and M-type stars, which are the most common type in our galaxy, have habitable zones located much closer to their surfaces, with potentially habitable planets orbiting at distances that would place them in tidally locked configurations, with one side permanently facing the star. These smaller stars also tend to be more active, emitting frequent flares and high-energy radiation that could strip away planetary atmospheres and bombard surfaces with harmful particles, potentially challenging the development of life, even for planets located within the theoretical habitable zone. The concept of the continuously habitable zone adds another layer of complexity to our understanding of planetary habitability, accounting for the fact that stars evolve over time, gradually increasing in luminosity as they age. This evolution means that the habitable zone migrates outward over the lifetime of a star, with planets that were initially too hot potentially becoming more temperate as their host star ages, while those that began in comfortable conditions might eventually become too hot for liquid water. For Earth, this gradual brightening of the sun suggests that our planet has perhaps 1 billion years or so remaining before the increasing solar radiation pushes it beyond the outer edge of the habitable zone, eventually leading to the evaporation of our oceans and the end of life as we know it. This temporal dimension of habitability reminds us that the conditions suitable for life are not static, but rather represent a temporary window in the long evolution of planetary systems. The traditional definition of the habitable zone has been challenged and refined in recent years, as we've discovered the remarkable diversity of exoplanets and gained a deeper understanding of the complex factors that influence planetary climates. One limitation of the classic habitable zone concept is its focus on the possibility of liquid water on the surface, potentially overlooking subsurface environments that might harbour life, despite surface conditions being inhospitable. The moons of Jupiter and Saturn in our own solar system demonstrate this possibility, with Europa and Enceladus likely containing vast subsurface oceans of liquid water, despite being located far outside the traditional habitable zone. This expanded view of habitability suggests that we should consider a broader range of environments when searching for life beyond Earth, including those that might be hidden from view beneath icy crusts or deep within planetary interiors. Super-Earths introduce additional complexities to our understanding of the habitable zone, as their greater mass and potentially different compositions could significantly influence their atmospheric retention and climate regulation compared to Earth-sized planets. The stronger gravitational fields of super-Earths might help them retain thicker atmospheres that could provide enhanced protection against stellar radiation and more effective greenhouse warming, potentially extending the outer boundary of the habitable zone for these worlds. Conversely, the higher surface pressures on super-Earths could also lead to different atmospheric circulation patterns and cloud formation processes that might affect their energy balance and climate stability in ways we are only beginning to understand. These factors suggest that the habitable zone for super-Earths might differ from that of Earth-sized planets, potentially encompassing a broader range of orbital distances depending on the specific characteristics of each world. The discovery of numerous super-Earths within the habitable zones of their host stars has been one of the most exciting developments in exoplanet research, providing tangible targets for future observations and the search for biosignatures. Among the most notable examples is Kepler 186f, a super-Earth with a radius approximately 1.1 times that of Earth, orbiting within the habitable zone of an M-type star located about 500 light-years from our solar system. This world receives roughly 1/3 of the energy from its star that Earth receives from the Sun, placing it near the outer edge of the habitable zone. But its potentially thicker atmosphere could help maintain temperatures suitable for liquid water. Another intriguing example is LHS 1140b, a super-Earth about 1.4 times the radius of Earth orbiting within the habitable zone of a small, cool star just 40 light-years away, making it one of the most promising targets for atmospheric characterization with current and upcoming telescopes. The TRAPPIST-1 system presents perhaps the most remarkable collection of potentially habitable super-Earths discovered to date, with 7 Earth-sized planets orbiting a small, ultra-cool dwarf star about 40 light-years away, 3 of which are located within the habitable zone. These worlds are likely tidally locked to their host star, with permanent day and night sides creating extreme temperature differences that could challenge the development of life as we know it. However, the presence of atmospheres sufficient to transport heat from the day side to the night side could potentially moderate these temperature extremes, creating more temperate conditions across at least portions of these planets' surfaces. The compact nature of this system, with all 7 planets orbiting closer to their star than Mercury orbits our Sun, demonstrates the remarkable diversity of planetary architectures that can exist within habitable zones and challenges our preconceptions about where and how potentially habitable worlds might form. The study of habitable zones around different types of stars has revealed that M-dwarf stars, despite their small size and lower temperatures, might actually offer the most promising environments for the detection of potentially habitable super-Earths in the near future. These stars, which make up approximately 75% of all stars in our galaxy, have habitable zones located very close to their surfaces, resulting in more frequent transits and stronger radial velocity signals that make orbiting planets easier to detect and characterize. Additionally, the relative abundance and longevity of M-dwarf stars, with lifespans that can extend for trillions of years, provide ample time for life to potentially emerge and evolve on planets orbiting within their habitable zones. These factors have made M-dwarf systems prime targets for current and upcoming exoplanet surveys, with several potentially habitable super-Earths already identified around these small, numerous stars. The atmospheric composition of a planet plays a crucial role in determining its position within the habitable zone, with different mixtures of gases creating varying degrees of greenhouse warming that can significantly extend or contract the region where liquid water might exist. A planet with a dense atmosphere rich in greenhouse gases like carbon dioxide or methane could maintain liquid water at much greater distances from its host star than a planet with a thin atmosphere similar to Earth's. Conversely, a planet with minimal atmospheric greenhouse warming would need to orbit closer to its star to maintain temperatures suitable for liquid water, potentially placing it at risk of experiencing a runaway greenhouse effect if stellar radiation increases even slightly. This complex interplay between atmospheric composition and stellar radiation underscores the limitations of defining habitable zones based solely on orbital distance, highlighting the need for more nuanced models that account for the specific characteristics of each planetary system. The concept of the habitable zone continues to evolve as we gain a deeper understanding of the complex factors that influence planetary climates and the potential for life to exist in diverse environments. Recent research has suggested that atmospheric processes such as cloud formation, which can both cool a planet by reflecting sunlight and warm it by trapping heat, could significantly expand the traditional boundaries of the habitable zone under certain conditions. Similarly, the presence of oceans and continents can affect a planet's energy balance through differences in heat capacity and albedo, creating regional climate variations that might allow for locally habitable conditions, even when global average temperatures fall outside the traditional habitable zone. These refinements to our understanding of planetary habitability remind us that the search for life beyond Earth requires a flexible and open-minded approach, one that considers the full spectrum of possible environments where life might emerge and persist. As we continue to discover and characterize super-Earths within the habitable zones of their host stars, each new world adds to our understanding of the diverse conditions that might support life beyond our solar system. The detection of biosignatures, chemical imbalances in planetary atmospheres that could potentially indicate biological activity, represents the next frontier in the study of potentially habitable super-Earths, with upcoming telescopes and instruments designed to analyze the atmospheric compositions of these worlds in unprecedented detail. The search for such signatures will require careful consideration of the complex interplay between stellar radiation, atmospheric chemistry, and planetary characteristics that define the habitable zone, as well as the development of sophisticated models to distinguish true biosignatures from abiotic processes that might produce similar chemical patterns. Each step forward in this quest brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Or does life exist in some form on the countless worlds that orbit distant stars throughout our galaxy? The atmospheres of super-Earths represent perhaps the most critical factor in determining their potential to host life, serving as both protective shields and climate regulators that shape surface conditions in profound ways. These gaseous envelopes, which can vary dramatically in composition, density, and extent, play a central role in maintaining the delicate balance of factors that allow for the existence of liquid water and the complex chemistry that underlies life as we know it. Unlike Earth, with its relatively thin atmosphere dominated by nitrogen and oxygen, super-Earths might retain significantly thicker atmospheres due to their stronger gravitational fields, potentially creating surface pressures many times greater than what we experience on our planet. This enhanced atmospheric retention could prove beneficial for maintaining stable climates over geological timescales, protecting surfaces from harmful radiation, and providing the raw materials necessary for the emergence and evolution of life. The composition of super-Earth atmospheres presents a fascinating spectrum of possibilities, influenced by numerous factors, including the planet's formation history, distance from its host star, geological activity, and interactions with the space environment. Some super-Earths might have atmospheres similar to Earth's, with nitrogen as the primary component and oxygen as a reactive gas produced by biological processes, while others could be dominated by carbon dioxide, creating greenhouse conditions that maintain surface temperatures suitable for liquid water despite greater distances from their host stars. Still others might retain thick hydrogen envelopes from their formation, creating conditions quite different from anything in our solar system, with potentially profound implications for surface chemistry and the development of life. Understanding this diversity of atmospheric compositions is essential for assessing the potential habitability of these worlds and identifying the most promising targets for future observations in the search for life beyond Earth. The greenhouse effect, which warms Earth's surface by approximately 33 degrees Celsius through the trapping of heat by atmospheric gases, operates on all planets with atmospheres, but can vary dramatically in intensity depending on atmospheric composition and density. On super-Earths, this effect could be significantly enhanced or diminished compared to Earth, depending on the specific mix of greenhouse gases present and the total atmospheric pressure. A super-Earth with a dense carbon dioxide atmosphere might experience substantial greenhouse warming, potentially maintaining liquid water at distances from its host star, where a thinner atmosphere would result in a frozen world. Conversely, a super-Earth with minimal greenhouse gases in its atmosphere would need to orbit closer to its star to maintain temperatures suitable for liquid water, potentially placing it at risk of experiencing a runaway greenhouse effect if stellar radiation increases, or if additional greenhouse gases are released through geological processes. Atmospheric circulation patterns on super-Earths would likely differ from those on Earth due to factors including their stronger gravitational fields, potentially different rotation rates, and the possibility of tidal locking for planets orbiting close to small stars. These differences could create unique climate systems with wind patterns, precipitation cycles, and temperature distributions quite unlike those we experience on our planet. For tidally locked super-Earths, which always present the same face to their host star, atmospheric circulation would be particularly crucial for transporting heat from the perpetually illuminated day side to the dark night side, potentially creating more moderate temperatures across the surface than would otherwise be possible. The study of these atmospheric dynamics represents a complex but essential aspect of understanding the potential habitability of these worlds, as circulation patterns directly influence surface temperatures, weather systems, and the distribution of volatile compounds necessary for life. Cloud formation and behavior on super-Earths present another intriguing area of investigation, as these atmospheric phenomena play crucial roles in planetary energy balance and climate regulation. Clouds can both cool a planet by reflecting sunlight back into space and warm it by trapping heat radiating from the surface, with the net effect depending on cloud altitude, composition, and coverage. On super-Earths, different atmospheric compositions and pressures could lead to cloud types quite unlike those on Earth, potentially composed of alternative compounds such as sulfuric acid, ammonia, or various hydrocarbons, depending on local temperatures and chemical conditions. These exotic clouds would not only affect the planet's energy balance, but could also influence the transmission of starlight through the atmosphere, creating distinctive signatures that might be detectable with future telescopes and providing valuable information about atmospheric conditions on these distant worlds. The presence of water vapor in a planet's atmosphere represents one of the most promising indicators of potential habitability, as this simple molecule is essential for all known forms of life and plays a central role in climate regulation through the greenhouse effect and cloud formation. On super-Earths, located within the habitable zone of their host stars, water vapor could be a significant component of the atmosphere, participating in complex feedback loops that influence surface temperatures and the distribution of liquid water. The detection of water vapor in the atmosphere of a super-Earth would be a major step forward in our search for potentially habitable worlds, providing evidence that this crucial compound exists in significant quantities and is participating in atmospheric processes. Future space-based telescopes, such as the James Webb Space Telescope and planned next-generation observatories, will have the capability to search for water vapor and other molecules in the atmospheres of nearby super-Earths, bringing us closer to identifying worlds that might truly be capable of hosting life. Atmospheric retention represents a critical challenge for planetary habitability, particularly for planets orbiting active stars that emit high levels of radiation and stellar winds that can gradually strip away atmospheric gases over time. Super-Earths, with their stronger gravitational fields, might be better equipped than smaller planets to retain their atmospheres in the face of these erosive forces, potentially maintaining stable atmospheric conditions over billions of years. The ability to retain an atmosphere depends on numerous factors, including the planet's mass, magnetic field strength, the intensity of stellar radiation, and the composition of the atmosphere itself, with lighter gases like hydrogen and helium being more easily lost than heavier molecules such as nitrogen and oxygen. Understanding these atmospheric loss processes is essential for assessing the long-term habitability of super-Earths, as even planets that initially possess suitable conditions might become barren over time if their atmospheres are stripped away by stellar activity. The interaction between a planet's atmosphere and its surface geology creates a complex system of feedback loops that can significantly influence climate stability and the potential for life to emerge and persist. On Earth, the carbonate-silicate cycle acts as a global thermostat, regulating atmospheric carbon dioxide levels over geological timescales through the weathering of silicate rocks, the precipitation of carbonate minerals, and the release of carbon dioxide through volcanic activity. Similar processes might operate on super-Earths, though their greater mass and potentially different compositions could lead to variations in the efficiency and operation of these geological feedback mechanisms. The presence of liquid water, plate tectonics, or alternative geological processes could all influence how effectively a super-Earth regulates its atmospheric composition and surface temperature, with profound implications for its long-term habitability and the potential for life to develop and evolve. The search for biosignatures, chemical imbalances in planetary atmospheres that could potentially indicate biological activity, represents one of the most exciting frontiers in the study of super-Earth atmospheres. On Earth, the presence of oxygen in our atmosphere, produced primarily by photosynthetic organisms, creates a chemical disequilibrium with reduced gases like methane that would not persist without continuous biological replenishment. Similar atmospheric signatures on other worlds could potentially indicate the presence of life, though distinguishing true biosignatures from abiotic processes that might produce similar patterns remains a significant challenge. For super-Earths, the detection of potential biosignatures would require not only advanced telescopes capable of analyzing their atmospheric compositions, but also sophisticated models to interpret these observations in the context of each planet's specific conditions, including stellar radiation, geological activity, and atmospheric chemistry. The study of super-Earth atmospheres has been revolutionized by the development of transmission spectroscopy, a technique that analyzes the starlight filtering through a planet's atmosphere during transit events to identify specific molecules based on their absorption of particular wavelengths of light. This method has already been used to detect water vapor, methane, carbon monoxide, and other compounds in the atmospheres of some larger exoplanets, and upcoming telescopes promise to extend these capabilities to smaller super-Earths orbiting nearby stars. Each atmospheric detection adds to our understanding of the diversity of planetary atmospheres throughout the galaxy and provides insights into the processes that shape these gaseous envelopes over time. The refinement of these techniques represents a crucial step toward the ultimate goal of identifying potentially habitable worlds and searching for signs of life beyond our solar system. The climate stability of super-Earths over geological timescales represents another critical factor in their potential to host life, as the emergence and evolution of complex organisms typically requires periods of relative environmental stability, extending over millions or billions of years. Factors that could influence climate stability include the planet's orbital characteristics, the presence and operation of feedback mechanisms, like the carbonate-silicate cycle, the intensity of stellar radiation and its variation over time, and the planet's internal heat budget and geological activity. Super-Earths, with their greater mass, might maintain internal heat and geological activity for longer periods than smaller planets, potentially supporting climate-regulating processes for extended timescales. Finally, their stronger gravitational fields might help stabilize axial tilt variations that could cause dramatic climate shifts on less massive worlds, creating more predictable seasonal patterns and long-term climate conditions that could favor the development and persistence of life. The differential atmospheric conditions on super-Earths challenges us to expand our thinking about habitable environments beyond the Earth-centric models that have traditionally guided the search for life beyond our solar system. These worlds might host atmospheric compositions, pressures, and circulation patterns quite unlike any, yet still maintain conditions suitable for liquid water and the complex chemistry that underlies life as we know it. The possibility of hydrogen-dominated atmospheres on some super-Earths, for example, presents a scenario radically different from Earth's nitrogen-oxygen atmosphere, yet theoretical studies suggest that such environments could potentially support novel forms of biochemistry under certain conditions. This expanded view of habitability reminds us that life might adapt to a much wider range of environments than we previously imagined, and that the search for life beyond Earth should be guided by principles of chemical and thermodynamic possibility, rather than by strict analogy to conditions on our own planet. As we continue to study and characterize the atmospheres of super-Earths, each new discovery adds to our understanding of the complex interplay between planetary characteristics, atmospheric processes, and the potential for life to exist in diverse environments throughout the cosmos. The development of increasingly sophisticated models of atmospheric physics and chemistry, combined with observations from current and upcoming telescopes, will gradually reveal the rich diversity of atmospheric conditions that exist on these worlds. This growing knowledge will not only enhance our understanding of planetary science, but will also inform the search for life beyond Earth, helping us identify the most promising targets for future exploration and observation. The atmospheres of super-Earths represent both a frontier of scientific discovery and a window into the potential prevalence of life in the universe, offering insights that may ultimately answer one of humanity's most profound questions about our place in the cosmos. The intricate dance between a planet's interior and surface creates the foundation upon which habitable environments can emerge and thrive, with geological processes playing a crucial role in regulating climate, cycling essential elements, and maintaining the conditions necessary for life. On Earth, plate tectonics has been instrumental in creating a stable climate over billions of years, facilitating the carbon-silicate cycle that acts as a global thermostat, regulating atmospheric carbon dioxide levels through the weathering of rocks, the formation of carbonate minerals, and the release of gases through volcanic activity. This continuous recycling of material between the interior and surface helps maintain relatively stable temperatures, despite variations in solar radiation over geological timescales, creating the long-term environmental stability that likely enabled the emergence and evolution of complex life forms. The operation of these geological processes represents a delicate balance that may be essential for the development and persistence of life on a planetary scale. Super-Earths, with their greater mass and potentially different internal structures, might experience geological processes that differ significantly from those we observe on Earth, creating alternative pathways for maintaining habitable conditions over time. The higher pressures and temperatures within these worlds could lead to different patterns of mantle convection, potentially resulting in more vigorous geological activity or entirely different modes of surface renewal compared to plate tectonics. Some theoretical models suggest that larger planets might experience episodes of global resurfacing rather than continuous plate movement, with periods of intense volcanic activity completely overhauling the surface every few 100 million years. These alternative geological regimes could still provide the essential functions needed for habitability, such as the cycling of carbon between the atmosphere and interior, the regulation of surface temperature, and the creation of diverse environments that might foster biological complexity. The internal heat budget of a planet represents a fundamental factor influencing its geological activity and potential for maintaining habitable conditions over geological timescales. This heat originates from two primary sources: the primordial heat remaining from planetary formation and the ongoing radioactive decay of elements such as uranium, thorium, and potassium within the planet's interior. Super-Earths, with their greater volume relative to surface area, might retain internal heat more efficiently than smaller planets, potentially maintaining geological activity for longer periods or experiencing more intense volcanism and tectonics throughout their history. This enhanced internal heat could drive more robust mantle convection, potentially supporting active geology for billions of years longer than on Earth, creating extended windows of opportunity for life to emerge and evolve. The relationship between planetary mass, internal heat, and geological activity represents a crucial consideration in assessing the long-term habitability of super-Earths. The phenomenon of plate tectonics, which characterizes Earth's surface geology and plays a central role in maintaining our planet's habitability, might operate differently or not at all on super-Earths due to their greater mass and higher internal pressures. On Earth, the relatively thin lithosphere is broken into numerous plates that move slowly across the surface, driven by convection currents in the underlying mantle, creating a dynamic system of crust formation, subduction, and continental drift. The higher pressures within super-Earths could result in stronger, more viscous lithospheres that resist fracturing and subduction, potentially leading to stagnant lid tectonics, where the surface remains as a single unbroken plate, rather than dividing into moving plates. This alternative mode of surface geology might still facilitate some degree of chemical cycling between the interior and atmosphere through volcanic activity and other processes, though potentially less efficiently than plate tectonics, with implications for long-term climate stability and the regulation of atmospheric composition. Volcanism represents one of the most important geological processes influencing planetary habitability, releasing gases from the interior that contribute to atmospheric formation and evolution, while also creating diverse surface environments that might foster biological activity. On Earth, volcanic outgassing has been crucial for maintaining our atmosphere over geological time, replenishing gases that are gradually lost to space and providing the raw materials for the development of life. Super-Earths might experience different patterns of volcanic activity, depending on their internal structure and heat flow, with some potentially exhibiting more widespread or intense volcanism due to their greater internal heat and stronger gravitational fields. These volcanic emissions could significantly influence atmospheric composition and density, potentially creating thicker atmospheres than Earth's that provide enhanced protection against stellar radiation and more effective greenhouse warming, extending the outer boundaries of the habitable zone for these worlds. The formation and evolution of continental crust represents another geological process that could significantly influence the habitability of super-Earths, as continents play crucial roles in regulating climate, sea level, and the distribution of nutrients essential for life. On Earth, the differentiation between lighter continental crust and denser oceanic crust has created a diverse array of surface environments, from shallow marine regions to mountain ranges, each providing unique niches for biological colonization and evolution. Super-Earths might develop different patterns of crust formation depending on their internal structure and geological activity, potentially creating more uniform surfaces or alternative distributions of land and sea that would affect climate regulation and the potential for life. The presence or absence of continental-like features could influence atmospheric circulation patterns, weathering processes that regulate atmospheric carbon dioxide, and the availability of various chemical compounds that might be essential for the emergence and persistence of life. The magnetic fields generated by planetary cores represent another crucial geological factor influencing habitability, as these fields protect atmospheres from erosion by stellar winds and shield surfaces from harmful cosmic radiation that could damage biological molecules. On Earth, our magnetic field is generated by the motion of molten iron in the outer core, creating a protective magnetosphere that extends thousands of kilometers into space. Super-Earths, with their potentially larger iron cores and more rapid rotation rates, might generate even stronger magnetic fields than Earth's, offering enhanced protection to their surfaces and any potential life forms. This increased magnetic shielding could be particularly valuable for planets orbiting active stars that emit higher levels of radiation and charged particles, potentially expanding the range of stellar environments around which habitable super-Earths might exist. The interaction between geological processes and surface water creates complex feedback loops that can significantly influence planetary habitability over time, with water playing crucial roles in rock weathering, nutrient cycling, and the regulation of atmospheric composition. On Earth, the presence of liquid water facilitates chemical reactions that break down silicate rocks, a process that consumes atmospheric carbon dioxide and ultimately transfers it to the ocean floor, where it can be subducted and recycled through volcanic activity. This carbonate-silicate cycle has helped maintain relatively stable temperatures on Earth for billions of years, demonstrating the intimate connection between geological processes, surface conditions, and long-term habitability. Super-Earths, with their potentially different geological regimes, might experience variations in the efficiency of these feedback mechanisms, potentially leading to different patterns of climate regulation and atmospheric evolution that could influence their suitability for hosting life. The role of geological activity in creating and maintaining diverse surface environments represents another important consideration in assessing the habitability of super-Earths. As biological evolution often benefits from a variety of habitats and environmental conditions, on Earth, plate tectonics has created a dynamic surface with continually changing landscapes, from oceanic trenches to mountain ranges, each providing unique conditions that have driven evolutionary innovation and adaptation. Super-Earths experiencing different geological processes might develop alternative patterns of surface diversity, potentially creating more uniform landscapes or different distributions of environmental features that could influence the potential for biological complexity. The creation of varied surface environments through geological activity could be crucial for fostering the evolutionary processes that lead to complex life forms, suggesting that planets with active geology might be more likely to host diverse and sophisticated ecosystems. The timescales over which geological processes operate represent another crucial factor in planetary habitability, as the emergence and evolution of life typically require periods of relative environmental stability, extending over millions or billions of years. Earth's plate tectonic system has operated continuously for at least the past billion years, maintaining relatively stable conditions that allowed complex life to develop and diversify. Super-Earths might experience different patterns of geological activity over time, with some potentially exhibiting more episodic or variable rates of volcanism, tectonics, or other surface renewing processes. The long-term stability of geological activity on these worlds could significantly influence their potential for hosting complex life, with planets maintaining consistent geological processes over extended periods being more likely to provide the stable conditions necessary for biological evolution. Understanding these temporal patterns of geological activity represents an important aspect of assessing the habitability of super-Earths and their potential for hosting life beyond Earth. The study of geological processes on super-Earths remains largely theoretical at present, as our ability to directly observe the surface features of these distant worlds remains limited by current technological capabilities. However, advances in computational modeling and our understanding of planetary physics allow scientists to simulate the internal dynamics and surface processes of these worlds with increasing sophistication. These models suggest that super-Earths might exhibit a wide range of geological behaviors depending on their specific characteristics, including mass, composition, internal heat budget, and distance from their host star. As our observational capabilities improve with next-generation telescopes and instruments, we may eventually be able to detect indirect evidence of geological activity on these worlds, such as volcanic gases in their atmospheres or variations in surface temperature that might indicate ongoing tectonic processes. Each new discovery will add to our understanding of the complex relationship between planetary geology and the potential for life to exist in diverse environments throughout the cosmos. Water stands as perhaps the most fundamental requirement for life as we understand it, serving as the universal solvent in which the complex chemistry of biological processes can unfold. This simple molecule, composed of just 2 hydrogen atoms and 1 oxygen atom, possesses remarkable properties that make it uniquely suited for supporting life, including its ability to dissolve a wide range of substances, its high heat capacity that helps regulate temperature, and its unusual density behavior that allows ice to float, protecting liquid water below. On super-Earths, the presence of water in sufficient quantities and in appropriate forms could be the determining factor between a barren rock and a world teeming with potential biological activity. The distribution and state of water on these larger worlds might differ significantly from what we observe on Earth, creating environments that could expand our understanding of where and how life might exist in the universe. The various forms in which water might exist on super-Earths present a fascinating spectrum of possibilities, from familiar surface oceans to exotic high-pressure ice phases that do not occur naturally under Earth conditions. Some super-Earths might be true water worlds, with global oceans hundreds of kilometers deep covering their entire surfaces, potentially hiding any solid crust beneath vast aquatic realms. Others might have more Earth-like distributions of water, with oceans, ice caps, and atmospheric water vapor participating in complex hydrological cycles that influence climate and surface conditions. The most intriguing possibility is the existence of subsurface oceans on super-Earths, similar to what we suspect exists on moons like Europa and Enceladus in our solar system, where liquid water could be maintained far from stellar influence through tidal heating or radioactive decay, potentially creating habitats shielded from harsh surface conditions. The chemistry of life as we know it relies on a specific set of elements and molecular building blocks that must be available in appropriate forms and concentrations for biological processes to occur. Carbon stands as the backbone of life on Earth due to its unique ability to form stable, complex molecules with itself and other elements, creating the diverse organic compounds necessary for cellular structures, metabolic processes, and genetic information storage. On super-Earths, the availability of carbon and other biogenic elements, including hydrogen, oxygen, nitrogen, phosphorus, and sulfur, would be essential for the emergence of life, similar to what we find on our planet. The geological processes we discussed earlier play a crucial role in making these elements available through weathering, volcanic outgassing, and hydrothermal activity, creating the chemical environments where prebiotic chemistry might lead to the first stirrings of life. The potential for alternative biochemistries represents one of the most intriguing frontiers in our consideration of life on super-Earths, challenging our Earth-centric assumptions about what forms life might take. While carbon-based biochemistry in water solvent represents the only example we know of, scientists have theorized about other possibilities that might exist under the different conditions found on super-Earths. Silicon, which sits directly below carbon on the periodic table and shares some of its chemical properties, has been proposed as a potential alternative backbone for life, though its chemistry differs in important ways that might limit its suitability. Similarly, alternative solvents such as ammonia, methane, or ethane might support biological processes under the specific temperature and pressure conditions that could exist on some super-Earths, particularly those located farther from their host stars, where temperatures might be too low for liquid water, but suitable for other solvents. The extreme conditions that might exist on some super-Earths could give rise to exotic chemical processes and potentially novel forms of life that would be radically different from anything we have encountered on Earth. Higher surface pressures and stronger gravitational fields could influence molecular interactions and reaction rates in ways that might favor different biochemical pathways than those that evolved under Earth conditions. The possibility of hydrogen-dominated atmospheres on some super-Earths presents another intriguing scenario, as hydrogen can participate in a wide range of chemical reactions and might support metabolic processes, quite unlike those in oxygen-based life. These considerations remind us that life might adapt to a much broader range of chemical environments than we typically imagine, and that our search for life beyond Earth should be guided by principles of chemical possibility, rather than strict analogy to terrestrial biology. The detection of water and relevant chemical compounds on distant super-Earths represents one of the primary goals of current and future exoplanet observation programs, as these detections would provide crucial evidence about the potential habitability of these worlds. Spectroscopic analysis of light filtering through a planet's atmosphere during transit events can reveal the presence of water vapor and other molecules based on their characteristic absorption of specific wavelengths, offering clues about atmospheric composition and potential chemical processes occurring on the planet's surface. For planets that do not transit their host stars from our perspective, direct imaging combined with spectroscopy might eventually provide similar information, though this approach requires significantly more advanced technology than is currently available. Each new detection of water or biogenic elements in a super-Earth's atmosphere adds to our understanding of the distribution of these essential ingredients throughout the galaxy and helps identify the most promising targets for further study in the search for life. The concept of the habitable zone, which we discussed earlier, might need to be expanded to account for the diverse ways water and other essential compounds might exist and participate in chemical processes on super-Earths. Traditional definitions focus on the possibility of liquid water on a planet's surface, but we now recognize that subsurface environments maintained by internal heat could potentially host liquid water far outside this zone, as could worlds with thick atmospheres that create sufficient greenhouse warming to maintain liquid water at greater distances from their host stars. Additionally, the possibility of alternative solvents suggests that habitable environments might exist in temperature ranges quite different from those suitable for liquid water, potentially expanding the range of stellar environments around which life might emerge. This more nuanced view of habitability acknowledges the complex interplay between planetary characteristics, stellar conditions, and chemical possibilities that determine whether a world might support life. The chemical evolution that leads from simple abiotic compounds to complex biological systems represents one of the greatest mysteries in science, and understanding how this process might occur on super-Earths is essential for assessing their potential for hosting life. On Earth, the transition from prebiotic chemistry to the first living organisms likely occurred in environments such as hydrothermal vents, tidal pools, or clay mineral surfaces, where energy sources, catalytic materials, and appropriate chemical conditions combine to facilitate the formation of increasingly complex organic molecules. Super-Earths might offer different environments for this chemical evolution, with their potentially different geological activity, atmospheric composition, and surface conditions, creating alternative pathways from chemistry to biology. The study of these possibilities not only informs our search for life beyond Earth, but also helps us understand the fundamental principles that might govern the emergence of life, wherever suitable conditions exist. The interaction between water and rock on planetary surfaces creates complex chemical environments that can influence the availability of nutrients and energy sources essential for life, a process that might operate differently on super-Earths due to their greater mass and potentially different geological activity. On Earth, weathering processes break down silicate minerals, releasing elements that can be used by living organisms while also consuming atmospheric carbon dioxide in reactions that help regulate climate over geological timescales. The higher pressures and temperatures within super-Earths could lead to different mineral stabilities and reaction rates, potentially altering the efficiency of these weathering processes and the availability of various chemical compounds. These differences might result in distinct patterns of nutrient cycling and chemical evolution that could influence the trajectory of biological development on these worlds, potentially leading to biochemical innovations, quite unlike those that characterize life on Earth. The search for evidence of past or present water activity on super-Earths represents a crucial aspect of assessing their potential habitability, as the presence of water in appropriate forms is essential for life as we know it. While we cannot currently directly observe surface features on these distant worlds, indirect evidence might be obtained through atmospheric analysis, which can reveal the presence of water vapor and other compounds that indicate active hydrological cycles. Future telescopes with greater sensitivity and resolution might eventually be able to detect surface features such as oceans, ice caps, or seasonal variations that could provide more direct evidence of water activity. Each new observation adds to our understanding of how water is distributed throughout planetary systems and helps refine our models of which worlds might be most likely to host environments suitable for life, guiding future exploration and the development of more sophisticated detection methods. The potential for water to exist in multiple phases simultaneously on super-Earths creates complex environments that might foster diverse chemical processes and potentially multiple habitats for life within a single planetary system. On Earth, the coexistence of solid, liquid, and gaseous water creates dynamic interfaces where energy and nutrients are exchanged, driving complex chemical and biological processes. Super-Earths, with their potentially different temperature and pressure profiles, might exhibit even more complex distributions of water phases, creating unique environments where chemical reactions could occur under conditions not found on Earth. These diverse chemical environments might support multiple forms of life with different biochemical requirements, or they might facilitate the chemical evolution that leads from simple compounds to the complex systems characteristic of living organisms. Understanding these possibilities requires sophisticated models of planetary chemistry and climate that account for the unique characteristics of super-Earths. The chemistry of atmospheres on super-Earths might provide crucial clues about surface conditions and potential biological activity, as atmospheric composition reflects both the sources of gases from the planet's interior and surface processes that might consume or modify these compounds. On Earth, the presence of oxygen in our atmosphere at levels far exceeding chemical equilibrium represents a potential biosignature, as this reactive gas is continuously replenished by photosynthetic organisms. Similar chemical imbalances in the atmospheres of super-Earths might indicate biological activity, though distinguishing true biosignatures from abiotic processes that might produce similar patterns remains a significant challenge. The detection of specific combinations of gases, such as oxygen and methane or other pairs that would react with each other in the absence of continuous replenishment, could provide particularly compelling evidence for biological processes, though careful consideration of each planet's specific conditions would be essential for accurate interpretation. The study of extremophiles on Earth, organisms that thrive in environments previously considered inhospitable to life, has dramatically expanded our understanding of the range of conditions under which biological processes can occur, with important implications for our assessment of super-Earth habitability. These remarkable organisms have been found in environments ranging from deep-sea hydrothermal vents with temperatures exceeding 120 degrees Celsius to the highly acidic waters of volcanic hot springs and the frozen valleys of Antarctica, demonstrating life's extraordinary adaptability to extreme conditions. The existence of such organisms suggests that life on super-Earths might adapt to the potentially higher pressures, different atmospheric compositions, and alternative chemical environments that might exist on these worlds. This expanded view of biological possibility encourages us to consider a broader range of super-Earths as potentially habitable, including those with conditions quite different from those on Earth. The chemical building blocks necessary for life might be delivered to super-Earths through various processes, including the accretion of material during planetary formation, the ongoing influx of interplanetary dust and cometary material, and the production of compounds through atmospheric chemistry driven by stellar radiation. On Earth, the late heavy bombardment period, approximately 4 billion years ago, likely delivered significant quantities of water and organic compounds to our planet, potentially providing essential ingredients for the emergence of life. Similar processes might occur on super-Earths, with the efficiency and timing of these deliveries influencing the potential for life to develop. Additionally, the stronger gravitational fields of super-Earths might make them more effective at capturing and retaining material from space, potentially enhancing the delivery of water and prebiotic compounds compared to smaller planets. These considerations highlight the complex interplay between planetary characteristics and the availability of essential chemical ingredients for life. The potential for life to exist in environments with different water chemistry on super-Earths presents another fascinating area of speculation, as the salinity, pH, and dissolved mineral content of water can significantly influence biological processes. On Earth, organisms have adapted to a wide range of aquatic conditions, from the freshwater environments of lakes and rivers to the hypersaline waters of salt lakes and the highly alkaline or acidic conditions of certain extreme environments. Super-Earths might host water bodies with quite different chemical compositions depending on their geological history, atmospheric conditions, and the weathering processes that occur on their surfaces. These alternative aquatic environments might favor different biochemical pathways or support organisms with unique adaptations to their specific chemical conditions, potentially leading to forms of life quite unlike those we find on Earth. Understanding these possibilities requires careful consideration of how planetary characteristics influence water chemistry and how different chemical environments might affect the development and evolution of biological systems. The search for evidence of water and relevant chemical processes on super-Earths will benefit greatly from the next generation of space telescopes and ground-based observatories currently under development, which will provide unprecedented capabilities for analyzing the atmospheres of these distant worlds. Instruments such as the James Webb Space Telescope, already operational, and planned future missions, like the Habitable Exoplanet Observatory, will be able to detect the spectral signatures of water vapor and other compounds in the atmospheres of nearby super-Earths, providing crucial information about their potential habitability. These observations will help refine our understanding of how water and biogenic elements are distributed throughout planetary systems, and which worlds might be most likely to host environments suitable for life. Each new detection adds to our growing knowledge of the chemical diversity that exists in the cosmos and brings us closer to answering fundamental questions about the prevalence of life beyond Earth and the various forms it might take in environments quite different from our own. In the vast constellation Cygnus, approximately 500 light-years from our own world, exists a planet that has captured the imagination of astronomers and dreamers alike since its discovery in 2014. This world, known as Kepler 186f, orbits a star smaller and cooler than our Sun, yet maintains a position within its system that has led scientists to describe it as Earth's cosmic cousin. The planet was detected by NASA's Kepler Space Telescope, which observed the subtle dimming of starlight as the planet passed in front of its host star, revealing its presence and providing crucial data about its size and orbital characteristics. This remarkable discovery marked one of the first times a planet of similar size to Earth had been found within the habitable zone of its star, opening new possibilities in the search for potentially habitable worlds beyond our solar system. Kepler 186f has a radius only about 11% larger than Earth's, placing it firmly in the category of super-Earths, despite its relatively modest size compared to many other worlds in this classification. This similarity in size suggests that Kepler 186f might have a composition comparable to Earth's, with a rocky surface and potentially similar internal structure, though definitive confirmation of its composition remains beyond our current observational capabilities. The planet orbits its host star, Kepler 186, every 129.9 Earth days, receiving approximately 32% of the energy that Earth receives from the Sun, placing it near the outer edge of the habitable zone where liquid water could exist on its surface. This delicate balance of stellar radiation suggests that Kepler 186f might maintain temperatures suitable for liquid water, assuming it possesses an atmosphere sufficient to provide adequate insulation and pressure. The host star of this intriguing world, Kepler 186, is an M-dwarf star, also known as a red dwarf, which is the most common type of star in our Milky Way galaxy. These stars are smaller, cooler, and longer-lived than stars like our Sun, with lifespans that can extend for hundreds of billions or even trillions of years, providing ample time for life to potentially emerge and evolve on orbiting planets. Kepler 186 has about half the mass and radius of our Sun, with a surface temperature of approximately 3,788 Kelvin, compared to the Sun's 5,778 Kelvin, resulting in the distinctive reddish-orange hue that characterizes M-dwarf stars. The system containing Kepler 186f is approximately 5 billion years old, significantly older than our solar system, suggesting that any biological processes on the planet would have had considerable time to develop and potentially diversify into complex forms. The planetary system of Kepler 186 contains 4 other known planets, all of which orbit closer to their host star than Kepler 186f, and are likely too hot to maintain liquid water on their surfaces. These inner planets, designated Kepler 1, 86b, c, d, and e, have orbital periods ranging from just under 4 days to approximately 22 days, indicating that they are tidally locked to their star, with the same side perpetually facing the stellar surface. The architecture of this system, with multiple small planets in close orbits, followed by a potentially habitable world farther out, represents a configuration quite different from our solar system, but increasingly common among the exoplanetary systems discovered by the Kepler mission. This arrangement provides valuable insights into the diverse ways planetary systems can form and evolve, challenging our preconceptions based on the architecture of our own cosmic neighborhood. One of the most intriguing questions about Kepler 186f concerns its potential for being tidally locked to its host star, a condition that affects many planets orbiting in the habitable zones of M-dwarf stars due to their close proximity to to these smaller stars. Tidal locking would result in one hemisphere of the planet perpetually facing the star, experiencing constant daylight, while the other hemisphere would remain in perpetual darkness, with a terminator region of twilight between these two extremes. This configuration would create dramatic temperature differences across the planet's surface, potentially resulting in extreme weather patterns and atmospheric circulation as the atmosphere attempts to redistribute heat from the day side to the night side. However, the presence of a sufficiently thick and dynamic atmosphere could potentially moderate these temperature extremes, creating more temperate conditions across at least portions of the planet's surface and expanding the range of environments that might be suitable for life. The atmosphere of Kepler 186f remains one of the greatest mysteries surrounding this distant world, as our current observational capabilities have not yet allowed us to directly detect or analyze its atmospheric composition. The existence and nature of an atmosphere would profoundly influence the planet's surface conditions, with a thick atmosphere potentially providing sufficient greenhouse warming to maintain liquid water, despite receiving only about 1/3 of the stellar energy that Earth receives from the Sun. Conversely, if Kepler 186f lacks a substantial atmosphere, its surface might be frozen and inhospitable despite its position within the habitable zone. The composition of any potential atmosphere would also be crucial, with the presence of greenhouse gases such as carbon dioxide or methane playing a significant role in determining surface temperatures and the potential for liquid water to exist in stable form on the planet's surface. The potential surface conditions on Kepler 186f represent another area of intense scientific speculation, as the planet's greater mass compared to Earth might result in different geological and environmental conditions than those we experience on our world. With a mass estimated to be between 1.4 and 1.8 times that of Earth, Kepler 186f would have stronger surface gravity, potentially affecting everything from the height of mountains to the behavior of liquids and gases on its surface. This stronger gravity might also help the planet retain a thicker atmosphere than Earth, providing enhanced protection against stellar radiation and more effective heat distribution across the surface. The planet's geology could be similarly influenced by its greater mass, potentially resulting in more vigorous tectonic activity or volcanic processes that could play crucial roles in regulating atmospheric composition and climate over geological timescales. The discovery of Kepler 186f has had a profound impact on our understanding of planetary systems and the potential prevalence of habitable environments throughout the galaxy, demonstrating that Earth-sized planets can exist within the habitable zones of stars smaller than our Sun. This finding has expanded the range of stellar environments considered potentially capable of hosting habitable worlds, suggesting that the most common type of star in our galaxy might also be the most likely to harbour planets with conditions suitable for life as we know it. The detection of Kepler 186f has also provided valuable data for refining models of planetary formation and evolution, particularly regarding the factors that influence the development of rocky planets in the habitable zones of M-dwarf stars. Each new piece of information about this distant world contributes to our growing understanding of the diverse planetary systems that populate our galaxy and the various conditions that might support the emergence and persistence of life beyond Earth. The methods used to detect and characterize Kepler 186f represent the cutting edge of astronomical observation and analysis, showcasing the remarkable precision achievable with modern space-based telescopes and data analysis techniques. The Kepler Space Telescope monitored the brightness of Kepler 186 and approximately 150,000 other stars continuously for 4 years, searching for the minute periodic dimmings that indicate the presence of transiting planets. Detecting the transit signal of Kepler 186f required extraordinary precision, as the planet blocks only about 0.02% of its host star's light during each transit, a diminution comparable to the dimming caused by a single gnat passing in front of a car headlight from several miles away. The analysis of these subtle signals involved sophisticated algorithms to distinguish true planetary transits from various sources of noise and false positives, including stellar variability, instrumental effects, and background eclipsing binary stars. The significance of Kepler 186f in the search for life beyond Earth extends beyond its physical characteristics and orbital parameters, as it represents one of the most promising targets for future observations with more advanced telescopes and instruments. Upcoming space-based observatories, such as the James Webb Space Telescope and planned next-generation missions, may eventually be capable of analyzing the atmosphere of Kepler 186f, searching for chemical signatures that might indicate biological activity. These observations would focus on detecting potential biosignatures, such as oxygen, methane, or other gases that might exist in chemical disequilibrium, which could suggest the presence of biological processes similar to those that maintain Earth's atmosphere in its current state. While such observations remain beyond our current capabilities, the prospect of studying the atmosphere of an Earth-sized planet in the habitable zone of another star represents one of the most exciting frontiers in astronomical research and the search for life beyond our solar system. The public fascination with Kepler 186f reflects humanity's enduring curiosity about our place in the cosmos and the possibility that we might not be alone in the universe. Since its discovery, this distant world has captured the popular imagination, inspiring countless artistic renderings and speculative descriptions of what conditions might be like on its surface. These depictions range from Earth-like environments with oceans and continents to more alien landscapes adapted to the unique conditions of orbiting a red dwarf star, including vegetation that might appear black rather than green to more efficiently absorb the predominantly red light from its host star. While these artistic interpretations remain speculative, they reflect the profound impact that discoveries like Kepler 186f have on our collective consciousness, challenging us to expand our conception of what constitutes a habitable world, and encouraging us to contemplate the remarkable diversity of planets that exist throughout our galaxy. The study of Kepler 186f has also prompted scientists to reconsider the factors that determine planetary habitability, leading to more nuanced models that account for the complex interplay between stellar characteristics, planetary properties, and atmospheric conditions. Traditional definitions of the habitable zone, based primarily on the amount of stellar radiation a planet receives, have been refined to incorporate additional factors, including the planet's mass, atmospheric composition, geological activity, and the specific characteristics of its host star. For Kepler 186f, these considerations suggest that even though it receives less stellar energy than Earth, it might still maintain habitable conditions if it possesses a sufficiently thick atmosphere with an appropriate composition to provide adequate greenhouse warming. This more comprehensive approach to assessing habitability reflects our growing understanding of the complex factors that influence whether a planet might support life, moving beyond simple Earth-centric models to embrace the diverse possibilities that might exist throughout the cosmos. The discovery of Kepler 186f has also stimulated interest in the potential for life around M-dwarf stars, which were previously considered less likely hosts for habitable worlds due to their high levels of stellar activity, including frequent flares and coronal mass ejections that could potentially strip away planetary atmospheres. However, the detection of multiple potentially habitable planets around these stars has prompted scientists to reconsider the resilience of planetary atmospheres and the various factors that might protect them from stellar erosion. For Kepler 186f, factors such as its stronger magnetic field, potentially generated by its larger iron core, and its position farther from its host star might help mitigate the effects of stellar activity, allowing it to maintain a stable atmosphere over geological timescales. These considerations have expanded our understanding of the range of stellar environments that might support habitable worlds, suggesting that the most common type of star in our galaxy might also be the most likely to harbour planets with conditions suitable for life. As we continue to study Kepler 186f and other potentially habitable super-Earths, each new observation adds to our understanding of the complex factors that influence planetary habitability and the potential for life to exist in diverse environments throughout the cosmos. The development of increasingly sophisticated telescopes and instruments promises to gradually reveal more details about these distant worlds, including their atmospheric compositions, surface conditions, and potential geological activity. Each technological advancement brings us closer to answering fundamental questions about our place in the universe and the prevalence of life beyond Earth. With Kepler 186f serving as both a specific target for future study and a symbol of the remarkable progress we have made in exploring worlds beyond our solar system. The ongoing exploration of this Earth-sized planet in the habitable zone of a distant star represents one of the most compelling frontiers in human knowledge, challenging us to expand our understanding of what constitutes a habitable world and inspiring us to continue the search for life in the vast expanse of the cosmos. In the constellation Aquarius, approximately 40 light-years from Earth, exists a remarkable planetary system that has captivated astronomers and the public alike since its discovery in 2017. This system, known as TRAPPIST-1, consists of 7 Earth-sized planets orbiting an ultra-cool dwarf star, so small and dim that it appears only slightly larger than Jupiter in our sky, despite being a star. The discovery of this compact family of worlds, with all 7 planets orbiting closer to their star than Mercury orbits our Sun, has challenged our understanding of planetary system architecture and expanded our conception of where potentially habitable environments might exist. The TRAPPIST-1 system represents one of the most extraordinary exoplanetary discoveries of recent years, offering unprecedented opportunities to study multiple Earth-sized planets that might harbour conditions suitable for life. The central star of this intriguing system, TRAPPIST-1, is an ultra-cool dwarf star with approximately 8% of the Sun's mass, and 11% 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 of its radius, making it only slightly larger than the planet Jupiter. Despite its small size, this star is relatively young by astronomical standards, with an estimated age between 3 and 8 billion years, providing ample time for life to potentially emerge and evolve on its orbiting planets. The star's low temperature, around 2,550 Kelvin, compared to the Sun's 5,778 Kelvin, results in its distinctive reddish appearance and emits most of its energy in the infrared portion of the spectrum, creating a fundamentally different radiation environment for its planets compared to what we experience in our solar system. These characteristics make TRAPPIST-1 representative of the most common type of star in our galaxy, suggesting that planetary systems like this one might be widespread throughout the cosmos. The 7 planets of the TRAPPIST-1 system are designated TRAPPIST-1b through TRAPPIST-1h in order of their distance from their host star, with orbital periods ranging from just 1.5 days for the innermost planet to approximately 18.8 days for the outermost. All 7 planets are similar in size to Earth, with radii ranging from about 0.75 to 1.09 times that of our planet, placing them in the category of super-Earths or sub-Neptunes, depending on their compositions. The compact nature of this system is truly remarkable, with all 7 planets orbiting within a distance less than 1/5 of the Mercury-Sun distance in our solar system, creating a celestial dance where the planets are so close to each other that they would appear as large as our moon, or even larger as skies. This tight orbital configuration has resulted in complex gravitational interactions between the planets, creating orbital resonances that have helped astronomers precisely determine their masses and densities. 3 of the TRAPPIST-1 planets, E, F, and G, are located within the system's habitable zone, where conditions might allow for the existence of liquid water on their surfaces, given appropriate atmospheric conditions. TRAPPIST-1e, the 4th planet from the star, receives approximately the same amount of stellar energy as Venus does from our Sun, while TRAPPIST-1, F, and G receive levels comparable to Earth and Mars, respectively. This range of stellar radiation within the habitable zone creates a spectrum of possible environments, from potentially Venus-like conditions on the inner edge to Mars-like conditions on the outer edge, with Earth-like possibilities in between. The presence of multiple potentially habitable planets in a single system provides an unprecedented opportunity to study how similar-sized worlds evolve under slightly different stellar radiation environments, offering insights into the factors that influence planetary habitability. The phenomenon of tidal locking represents one of the most significant factors influencing the potential habitability of the TRAPPIST-1 planets, as all 7 worlds are likely synchronized with their host star due to their close orbits. This tidal locking would result in each planet perpetually showing the same face to TRAPPIST-1, creating permanent day and night sides with extreme. The day sides of these planets would experience constant stellar radiation, potentially becoming extremely hot, while the night sides would be perpetually dark and frigid, with temperatures potentially dropping to levels where even atmospheric gases would freeze. However, the presence of atmospheres sufficient to transport heat from the day side to the night side could potentially moderate these temperature extremes, creating more temperate conditions in certain regions or at certain altitudes that might be suitable for liquid water and potentially life. The atmospheric compositions of the TRAPPIST-1 planets remain among the most compelling mysteries surrounding this system, as our current observational capabilities have not yet allowed us to directly detect or analyze their gaseous envelopes. The existence and nature of atmospheres on these worlds would profoundly influence their surface conditions and potential habitability, with thicker atmospheres potentially providing better heat distribution and protection against stellar activity. The planet's proximity to their host star and the star's tendency to emit frequent flares raise questions about atmospheric retention over time, as stellar winds and radiation could potentially strip away lighter atmospheric components. Understanding whether these planets have been able to maintain atmospheres throughout the system's history represents a crucial step in assessing their potential for hosting life, as atmospheres play essential roles in regulating surface temperatures, protecting against harmful radiation, and providing the chemical environment necessary for biological processes. The potential for water on the TRAPPIST-1 planets represents another area of intense scientific interest, as the presence of water in appropriate forms and quantities would be essential for life as we understand it. Preliminary studies suggest that several of the TRAPPIST-1 planets, particularly those in the habitable zone, might have densities consistent with rocky compositions that could include significant amounts of water. Some models indicate that these planets could be water worlds with global oceans hundreds of kilometers deep, while others might have more Earth-like distributions of water, with oceans, ice caps, and atmospheric water vapor participating in complex hydrological cycles. The detection of water vapor in the atmospheres of these worlds would represent a major step forward in confirming their potential habitability, and upcoming telescopes such as the James Webb Space Telescope may eventually be capable of making such detections, providing crucial insights into the distribution of this essential compound throughout the system. The gravitational interactions between the TRA-PPIST-1 planets have created a complex system of orbital resonances that has enabled astronomers to precisely determine their masses and densities with remarkable accuracy. These resonances occur when the orbital periods of neighboring planets form simple ratios, causing them to periodically align in ways that exert regular gravitational influences on each other. For the TRAPPIST-1 system, the planets form a resonant chain where the orbital periods of neighboring planets are in ratios of approximately 8 to 5, 5 to 3, 3 to 2, 3 to 2, 4 to 3, and 3 to 2, creating a remarkably stable configuration that has persisted for billions of years. This precise knowledge of the planet's masses and densities has allowed scientists to estimate their compositions, suggesting that they are likely rocky worlds with potentially varying amounts of water and other volatile compounds, providing valuable constraints for models of their internal structures and potential surface conditions. The discovery of the TRAPPIST-1 system has had a profound impact on our understanding of planetary system architecture, demonstrating that compact configurations with multiple Earth-sized planets can exist and remain stable over billions of years. Prior to this discovery, models of planetary formation suggested that such tightly packed systems would be dynamically unstable, with gravitational interactions between planets leading to collisions or ejections from the system over relatively short timescales. The existence and stability of the TRAPPIST-1 system has forced scientists to revise these models, considering new factors that might contribute to the formation and persistence of such compact planetary families. This finding has significant implications for our understanding of how common, potentially habitable environments might be throughout the galaxy, suggesting that systems with multiple Earth-sized planets could be more prevalent than previously thought, greatly expanding the potential real estate for life beyond our solar system. The study of the TRAPPIST-1 system has also prompted scientists to reconsider the potential for life around M-dwarf stars, which were previously considered less likely hosts for habitable worlds due to their high levels of stellar activity and the challenges posed by tidal locking. The discovery of multiple potentially habitable planets around TRA-PPIST-1 has demonstrated that Earth-sized worlds can form and persist in the habitable zones of these small stars, despite the potential challenges posed by their unique characteristics. Research into the resilience of planetary atmospheres around such stars has suggested various mechanisms that might protect these worlds from stellar erosion, including stronger magnetic fields generated by their larger iron cores and the potential for rapid atmospheric reformation following stellar flare events. These considerations have expanded our understanding of the range of stellar environments that might support habitable worlds, suggesting that the most common type of star in our galaxy might also be the most likely to harbour planets with conditions suitable for life. The TRAPPIST-1 system has become one of the most intensively studied exoplanetary systems since its discovery, with astronomers around the world using a variety of telescopes and techniques to gather as much information as possible about these remarkable worlds. Observations have been conducted using space-based telescopes, including the Hubble Space Telescope and the Spitzer Space Telescope, as well as numerous ground-based facilities equipped with advanced spectrographs and other instruments designed to detect and characterize exoplanets. These observations have helped refine our understanding of the system's architecture, the planet's orbital characteristics, and potential constraints on their atmospheric compositions and surface conditions. Each new study adds to our growing knowledge of this extraordinary system, gradually building a more comprehensive picture of the complex interactions between the planets and their host star, and the various factors that might influence their potential habitability. The public fascination with the TRAPPIST-1 system reflects humanity's enduring curiosity about our place in the cosmos, and the possibility that we might not be alone in the universe. Since its discovery, this remarkable system has captured the popular imagination, inspiring countless artistic renderings and speculative descriptions of what conditions might be like on its 7 worlds. These depictions range from Earth-like environments with oceans and continents to more alien landscapes adapted to the unique conditions of orbiting an ultra-cool dwarf star, including vegetation that might appear black rather than green to more efficiently absorb the predominantly red and infrared light from their host star. While these artistic interpretations remain speculative, they reflect the profound impact that discoveries like the TRAPPIST-1 system have on our collective consciousness, challenging us to expand our conception of what constitutes a habitable world and encouraging us to contemplate the remarkable diversity of planets that exist throughout our galaxy. The future study of the TRAPPIST-1 system promises to be one of the most exciting frontiers in exoplanet research, with upcoming telescopes and instruments offering the potential to revolutionize our understanding of these worlds. The James Webb Space Telescope, with its powerful infrared capabilities, is particularly well suited to studying the TRAPPIST-1 planets, as their host star emits most of its energy in the infrared portion of the spectrum where Webb operates. Observations with Webb and other upcoming facilities may eventually be capable of detecting the atmospheres of these planets, analyzing their compositions, and searching for potential biosignatures that might indicate biological activity. Each technological advancement brings us closer to answering fundamental questions about the potential for life beyond Earth, with the TRAPPIST-1 system serving as both a specific target for future study and a symbol of the remarkable progress we have made in exploring worlds beyond our solar system. The ongoing exploration of this extraordinary family of worlds represents one of the most compelling scientific endeavors of our time, challenging us to expand our understanding of planetary habitability and inspiring us to continue the search for life in the vast expanse of the cosmos. In the constellation Octans, approximately 40 light-years from our solar system, orbits a super-Earth that has emerged as one of the most promising candidates in the search for potentially habitable worlds beyond Earth. Discovered in 2017 by the Mirth South Telescope Array, LHS 1140b has captivated astronomers with its unique combination of characteristics that suggest it might be capable of hosting conditions suitable for life as we know it. This remarkable world, with a radius approximately 1.4 times that of Earth and a mass about 6.6 times greater, presents an intriguing opportunity to study a planet that straddles the boundary between Earth-sized rocky worlds and larger mini-Neptunes. The discovery of LHS 1140b has added another valuable piece to the puzzle of planetary habitability, offering insights into the diverse ways potentially life-supporting environments might exist throughout the galaxy. LHS 1140b orbits its host star, LHS 1140, every 24.7 Earth days, placing it in the habitable zone where liquid water could potentially exist on its surface, given appropriate atmospheric conditions. The planet receives approximately half the energy from its star that Earth receives from the Sun, positioning it near the middle of the habitable zone, where temperatures might be moderate enough to maintain liquid water, without experiencing the extreme greenhouse effects that could render a planet too hot for life. This orbital distance represents a delicate balance that could allow for the existence of stable liquid water over geological timescales, provided the planet possesses an atmosphere sufficient to provide adequate insulation and pressure. The planet's position within the habitable zone, combined with its other characteristics, has made it a prime target for future observations aimed at detecting and analyzing its atmosphere. The host star of this intriguing world, LHS 1140, is an M-dwarf star, also known as a red dwarf, with approximately 15% of the Sun's mass and 19% of its radius, making it significantly smaller and cooler than our own star. Despite its diminutive size, this star is relatively stable compared to many other M-dwarfs, exhibiting lower levels of the stellar flares and high-energy radiation that could potentially strip away planetary atmospheres over time. This relative stability is particularly significant for the potential habitability of LHS 1140b, as it suggests the planet might have been able to retain its atmosphere throughout the system's history, which is estimated to be at least 5 billion years old. The combination of a stable host star and the planet's position within the habitable zone creates conditions that could potentially support the long-term environmental stability necessary for the emergence and evolution of life. One of the most remarkable characteristics of LHS 1140b is its density, which suggests a composition dominated by rock and metal, similar to Earth, but with a significantly higher proportion of these materials due to its greater mass. Calculations based on the planet's measured radius and mass indicate a density approximately 2.3 times that of water. Consistent with a rocky world with an iron core comprising a substantial portion of its interior, this high-density composition distinguishes LHS 1140b from many other discovered super-Earths, which often have lower densities, suggesting significant amounts of volatile compounds or gases in addition to rock and metal. The planet's rocky nature makes it particularly interesting from the perspective of potential habitability, as it suggests the possibility of Earth-like geological processes and surface conditions that could support diverse environments suitable for life. The potential for LHS 1140b to retain a substantial atmosphere represents another crucial factor in assessing its habitability, as atmospheres play essential roles in regulating surface temperatures, protecting against harmful radiation, and providing the chemical environment necessary for biological processes. With its greater mass compared to Earth, LHS 1140b would have stronger surface gravity, potentially enabling it to retain a thicker atmosphere than our planet over geological timescales. This enhanced atmospheric retention could be particularly valuable given the planet's position around an M-dwarf star, as it might help protect the atmosphere from erosion by stellar winds and radiation. The existence of a substantial atmosphere would also facilitate more efficient heat distribution across the planet's surface. potentially moderating temperature differences that might otherwise create extreme environmental conditions, inhospitable to life as we know it. The phenomenon of tidal locking presents another important consideration for the potential habitability of LHS 1140b, as its relatively close orbit around its host star makes it likely that the planet is synchronized with its rotational period. This tidal locking would result in one hemisphere perpetually facing the star, experiencing constant daylight, while the other hemisphere would remain in perpetual darkness, creating extreme temperature differences between the two sides. However, the presence of a sufficiently thick and dynamic atmosphere could potentially redistribute heat from the day side to the night side, moderating these temperature extremes and creating more temperate conditions across at least portions of the planet's surface. Additionally, the terminator region, the boundary between day and night, might experience more moderate temperatures that could be particularly suitable for liquid water and potentially life, regardless of whether the planet is tidally locked or not. The age of the LHS 1140 system represents another significant factor in the planet's potential habitability, as the system is estimated to be at least 5 billion years old, providing ample time for life to potentially emerge and evolve. This extended timeline suggests that if LHS 1140b possesses conditions suitable for life, biological processes could have had sufficient time to develop from simple prebiotic chemistry to potentially complex organisms. The planet's advanced age also implies that it has been exposed to its host star's radiation and stellar activity for billions of years, allowing us to infer something about its ability to retain an atmosphere and maintain stable surface conditions over geological timescales. This longevity stands in contrast to some other potentially habitable exoplanets that orbit much younger stars, where the environment might still be in a state of flux that could challenge the development of life. The discovery and characterization of LHS 1140b have been made possible by advances in astronomical observation techniques, particularly the combination of transit and radial velocity methods that have allowed astronomers to determine both the planet's radius and mass with remarkable precision. The transit method, which detects the slight dimming of starlight as the planet passes in front of its host star, revealed LHS 1140b's existence and provided measurements of its radius and orbital period. Subsequent observations using the radial velocity method, which detects the wobble of the star caused by the gravitational pull of the orbiting planet, allowed astronomers to determine the planet's mass, enabling the calculation of its density and providing insights into its composition. This combination of observational techniques has created a more comprehensive picture of LHS 1140b than would be possible with either method alone, demonstrating the power of using multiple approaches to study distant worlds. The potential surface conditions on LHS 1140b represent an area of intense scientific speculation, as the planet's greater mass and potentially different atmospheric composition could result in environments quite different from those we experience on Earth. With surface gravity approximately 3.4 times that of Earth, LHS 1140b would have profoundly different geological and environmental conditions, potentially affecting everything from the height of mountains to the behavior of liquids and gases on its surface. This stronger gravity might also influence the planet's geological activity, potentially resulting in more vigorous tectonic processes or volcanic activity that could play crucial roles in regulating atmospheric composition and climate over geological timescales. The planet's surface might feature landscapes shaped by these enhanced gravitational forces, creating topography and environmental conditions that would be both familiar and alien compared to what we find on our own world. The study of LHS 1140b has prompted scientists to refine their models of planetary formation and evolution, particularly regarding the factors that influence the development of rocky planets in the habitable zones of M-dwarf stars. The planet's high density and rocky composition suggests that it formed in a region of the protoplanetary disk with sufficient solid material to accrete a substantial rocky core, potentially losing any primordial hydrogen-helium envelope early in its history. This formation scenario differs from that of many other super-Earths, which may have retained significant amounts of gases and volatile compounds, resulting in lower densities and potentially different surface conditions. Understanding the specific circumstances that led to the formation of LHS1140b can provide valuable insights into the diverse pathways of planetary evolution and the various factors that determine whether a planet might develop conditions suitable for life. The future study of LHS1140b promises to be one of the most exciting frontiers in exoplanet research, with upcoming telescopes and instruments offering the potential to revolutionize our understanding of this remarkable world. The James Webb Space Telescope, with its powerful infrared capabilities, is particularly well suited to studying LHS1140b, as its host star emits significant energy in the infrared portion of the spectrum where Webb operates. Observations with Webb and other upcoming facilities may eventually be capable of detecting the planet's atmosphere, analyzing its composition, and searching for potential biosignatures that might indicate biological activity. Each technological advancement brings us closer to answering fundamental questions about the potential for life beyond Earth, with LHS1140b serving as both a specific target for future study and a symbol of the remarkable progress we have made in exploring worlds beyond our solar system. The significance of LHS1140b in the search for life beyond Earth extends beyond its physical characteristics and orbital parameters, as it represents one of the most promising targets for future observations with more advanced telescopes and instruments. Its combination of a rocky composition, position within the habitable zone, and relatively stable host star creates a compelling case for the possibility of habitable conditions, making it a priority for atmospheric characterization efforts. The detection of specific atmospheric components, particularly those that might exist in chemical disequilibrium, such as oxygen and methane, could provide tantalizing evidence for biological processes similar to those that maintain Earth's atmosphere in its current state. While such observations remain challenging with current technology, the prospect of studying the atmosphere of a rocky super-Earth in the habitable zone of another star represents one of the most exciting frontiers in astronomical research and the search for life beyond our solar system. The public fascination with LHS 1140b reflects humanity's enduring curiosity about our place in the cosmos and the possibility that we might not be alone in the universe. Since its discovery, this distant world has captured the popular imagination, inspiring artistic renderings and speculative descriptions of what conditions might be like on its surface. These depictions range from Earth-like environments with oceans and continents to more alien landscapes adapted to the unique conditions of higher gravity and potentially different atmospheric composition. While these artistic interpretations remain speculative, they reflect the profound impact that discoveries like LHS1140b have on our collective consciousness, challenging us to expand our conception of what constitutes a habitable world, and encouraging us to contemplate the remarkable diversity of planets that exist throughout our galaxy. The ongoing exploration of this super-Earth in the habitable zone of a distant star represents one of the most compelling scientific endeavors of our time, inspiring us to continue the search for life in the vast expanse of the cosmos. In the constellation Leo, approximately 124 light-years from our solar system, orbits a super-Earth that has captured the attention of astronomers and astrobiologists alike, with tantalizing evidence suggesting the presence of water vapor in its atmosphere. Discovered in 2015 by NASA's K2 mission, the successor to the Kepler Space Telescope, K2-18b has emerged as one of the most compelling exoplanets in the search for potentially habitable worlds beyond our solar system. This remarkable world, with a radius approximately 2.6 times that of Earth and a mass about 8.6 times greater, orbits within the habitable zone of its host star, creating conditions that might allow for the existence of liquid water on its surface. The detection of water vapor in the planet's atmosphere in 2019 marked a significant milestone in exoplanet research, representing the first time this crucial compound has been definitively identified in the atmosphere of a habitable zone exoplanet. K2-18b orbits its host star, K2-18, every 33 Earth days, completing a year in just over a month by our calendar, while maintaining a position that allows it to receive levels of stellar radiation, similar to what Earth receives from the Sun. This fortuitous orbital placement places the planet squarely within the habitable zone, where liquid water could potentially exist, assuming appropriate atmospheric conditions are present to maintain sufficient surface pressure and temperature. The planet's equilibrium temperature is estimated to be approximately 265 Kelvin, or about -8 degrees Celsius, which would be too cold for liquid water on its surface, without the warming effects of an atmosphere containing greenhouse gases. The detection of water vapor in its atmosphere suggests that such greenhouse warming might indeed be occurring, potentially raising surface temperatures to levels that could support liquid water in certain regions or under specific conditions. The host star of this intriguing world, K2-18, is an M-dwarf star, also known as a red dwarf, with approximately 1/3 of the Sun's mass and 40% of its radius, making it significantly smaller and cooler than our own star. Despite its diminutive size, this star is relatively stable compared to many other M-dwarfs, exhibiting moderate levels of stellar activity that might not be as detrimental to planetary atmospheres as the more extreme behavior observed in some similar stars. The star's lower temperature results in it emitting most of its energy in the infrared portion of the spectrum, creating a fundamentally different radiation environment for K2-18b compared to what we experience in our solar system. This characteristic of M-dwarf stars, which are the most common type in our galaxy, suggests that potentially habitable environments might exist around a vast number of similar stellar systems throughout the cosmos. One of the most fascinating aspects of K2-18b is its position in what astronomers sometimes call the radius valley, an observed gap in the distribution of exoplanet sizes between approximately 1.5 and 2.0 Earth radii, where relatively few planets are found. With a radius of 2.6 Earth radii, K2-18b falls on the larger side of this gap, placing it in a category of planets that might be transitioning from rocky super-Earths to mini-Neptunes with substantial gaseous envelopes. This intermediate size raises intriguing questions about the planet's composition and structure, with models suggesting it could be either a rocky world with a thick hydrogen-rich atmosphere or a water world with a global ocean hundreds of kilometers deep covered by a steam atmosphere. The detection of water vapor in its atmosphere provides important constraints on these possibilities, suggesting that water plays a significant role in the planet's composition and atmospheric processes. The detection of water vapor in the atmosphere of K2-18b represents a landmark achievement in exoplanet research, marking the first time this crucial compound has been definitively identified in the atmosphere of a habitable zone exoplanet. This discovery was made using data from the Hubble Space Telescope, which analyzed the spectrum of starlight filtering through the planet's atmosphere during transit events, revealing the characteristic absorption signatures of water molecules. The presence of water vapor suggests that K218b might have conditions suitable for liquid water somewhere on or within the planet, though the exact location and form of this water remain subjects of ongoing research and debate. This detection has profound implications for the search for life beyond Earth, as water is universally recognized as one of the most essential ingredients for life as we understand it, playing crucial roles in biological processes and serving as the universal solvent in which the complex chemistry of life can unfold. The potential for K218b to be a water world represents one of the most exciting possibilities raised by the discovery of water vapor in its atmosphere, as such environments would be fundamentally different from anything in our solar system. A water world scenario would involve a planet with no distinct continents, where a global ocean hundreds of kilometers deep covers the entire surface, potentially extending all the way down to high-pressure ice layers that form under the extreme pressures found in the planet's interior. Under these conditions, the boundary between liquid water and high-pressure ice might occur at depths of tens or even hundreds of kilometers below the surface, creating a vast three-dimensional environment where life could potentially exist at various depths with different temperature and pressure conditions. This exotic scenario challenges our Earth-centric conceptions of habitable environments and suggests that life might adapt to a much wider range of planetary conditions than we previously imagined. The atmospheric composition of K2-18b extends beyond water vapor, with additional detections suggesting the presence of other molecules that provide further insights into the planet's nature and potential habitability. Analysis of the Hubble Space Telescope data has revealed evidence for hydrogen and helium in the planet's atmosphere, along with hints of other compounds, including methane and ammonia, though these detections remain less certain than that of water vapor. The presence of significant amounts of hydrogen and helium suggests that K218b might have retained a substantial primordial atmosphere from its formation, distinguishing it from terrestrial planets like Earth that have lost most of their original hydrogen and helium over time. This atmospheric composition has important implications for the planet's potential habitability, as hydrogen-rich atmospheres can create powerful greenhouse effects that might maintain liquid water at greater distances from a star than would otherwise be possible, while also potentially supporting alternative biochemical pathways, quite different from those that characterize life on Earth. The mass and radius of K2-18b allow astronomers to calculate its density, which provides valuable constraints on the planet's possible composition and internal structure. With a mass approximately 8.6 times that of Earth and a radius 2.6 times greater, K2-18b has a density about 2.7 times that of water, significantly lower than Earth's density of 5.5 times that of water. This lower density suggests that the planet contains substantial amounts of lighter elements and compounds in addition to rock and metal, with water being a prime candidate given its detection in the atmosphere. Models based on these parameters indicate that K2-18b could consist of a rocky core surrounded by a thick layer of water in various phases, potentially including liquid water, high-pressure ice, and water vapor in the atmosphere, creating what might be described as a Hycean world, a term coined to describe planets with hydrogen-rich atmospheres and extensive water layers below. The potential surface conditions on K2-18b remain a subject of intense scientific speculation and debate, as the planet's intermediate size and atmospheric composition create possibilities quite different from what we find on Earth. If K2-18b is indeed a water world with a global ocean, the surface conditions would be profoundly influenced by the immense pressure at the bottom of such an ocean, potentially creating exotic forms of ice that are denser than liquid water and preventing direct contact between the ocean and any rocky core that might exist beneath. The planet's stronger gravity, approximately 1.3 times that of Earth, would also affect everything from atmospheric circulation to ocean currents, creating environmental conditions that could be both familiar and alien compared to what we experience on our world. These unique conditions challenge us to expand our understanding of what constitutes a habitable environment, and to consider the diverse ways life might adapt to worlds quite different from our own. The discovery of water vapor in the atmosphere of K2-18b has stimulated renewed interest in the study of sub-Neptune planets and their potential for hosting habitable environments, challenging previous assumptions that such worlds would be inhospitable to life due to their thick atmospheres and potential lack of solid surfaces. This finding has prompted scientists to reconsider the factors that determine planetary habitability, moving beyond simple Earth-centric models to embrace a more nuanced understanding that accounts for the diverse ways planets might maintain conditions suitable for liquid water and the complex chemistry of life. The possibility that sub-Neptune planets like K2-18b could host habitable environments significantly expands the range of potentially life-bearing worlds in our galaxy, as this category of planet is among the most common types detected by exoplanet surveys. This expanded view of habitability has profound implications for the search for life beyond Earth, suggesting that we should look to a much broader range of planetary types than previously considered. The methods used to detect and characterize K2-18b represent the cutting edge of astronomical observation and analysis, showcasing the remarkable precision achievable with modern space-based telescopes and data analysis techniques. The initial detection of the planet was made by the K2 mission, which monitored the brightness of hundreds of thousands of stars, searching for the minute periodic dimmings that indicate the presence of transiting planets. The subsequent characterization of its atmosphere required even more sophisticated observations using the Hubble Space Telescope's Wide Field Camera 3, which captured the spectrum of starlight filtering through the planet's atmosphere during transit events. The analysis of these subtle spectral features involved advanced statistical techniques to distinguish true atmospheric signatures from various sources of noise and instrumental effects, demonstrating the extraordinary precision now achievable in exoplanet research. The future study of K2-18b promises to be one of the most exciting frontiers in exoplanet research, with upcoming telescopes and instruments offering the potential to revolutionize our understanding of this remarkable world. The James Webb Space Telescope, with its powerful infrared capabilities and much larger mirror than Hubble, is particularly well suited to studying K2-18b, as it will be able to obtain more detailed spectra of the planet's atmosphere, potentially revealing additional molecular components and providing better constraints on the planet's composition and structure. Observations with Webb and other upcoming facilities may eventually be capable of detecting more complex molecules in K2-18b's atmosphere, including potential biosignatures that might indicate biological activity. Each technological advancement brings us closer to answering fundamental questions about the potential for life beyond Earth, with K2-18b serving as both a specific target for future study and a symbol of the remarkable progress we have made in exploring worlds beyond our solar system. The significance of K2-18b in the search for life beyond Earth extends far beyond the detection of water vapor in its atmosphere, as this discovery has fundamentally altered our understanding of where and how potentially habitable environments might exist throughout the galaxy. This super-Earth has demonstrated that planets with sizes and atmospheric compositions quite different from Earth's might still maintain conditions suitable for liquid water and potentially life, challenging us to expand our conception of what constitutes a habitable world. The possibility that K218b might be a water world with a global ocean hundreds of kilometers deep represents one of the most exotic and potentially habitable environments yet discovered, suggesting that life might adapt to conditions far removed from those we find on our own planet. Each new discovery about this remarkable world adds to our growing understanding of the diverse ways planets might maintain habitable conditions, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe, or does life exist in some form on the countless worlds that orbit distant stars throughout our galaxy? In the constellation Cancer, approximately 40 light-years from our solar system, orbits a super-Earth that has captured the imagination of scientists and the public alike with its exotic composition and extreme environmental conditions. Discovered in 2004, 55 Cancri E is a world unlike any in our solar system, with characteristics that challenge our understanding of planetary formation and the diverse forms planets can take throughout the cosmos. This remarkable world, with a radius approximately twice that of Earth and a mass about 8 times greater, orbits so close to its host star that it completes a full revolution in less than 18 Earth hours, creating conditions that would be utterly inhospitable to life as we know it. The study of 55 Cancri E has expanded our conception of planetary diversity, revealing that the universe can produce worlds with compositions and environments far beyond what we might have imagined, based solely on our own solar system. 55 Cancri E orbits its host star. 55 Cancri A, at a distance of merely 0.0156 astronomical units, which is about 25 times closer than Mercury orbits our Sun, placing it in a realm of extreme heat and intense stellar radiation. This proximity results in surface temperatures estimated to reach approximately 2,700 Kelvin, or about 2,400 degrees Celsius, hot enough to melt most metals and vaporize rocks, creating a landscape that would be completely alien to human experience. The planet is tidally locked to its star, with one hemisphere perpetually facing the stellar surface, while the other remains in constant darkness. Though the extreme heat is likely distributed throughout the planet due to its thick atmosphere and efficient heat transfer mechanisms. These extraordinary conditions make 55 Cancri E a fascinating laboratory for studying the behavior of materials and planetary processes under environments far more extreme than any found in our solar system. One of the most intriguing aspects of 55 Cancri E is its composition, which evidence suggests may be unusually rich in carbon relative to the oxygen-dominated composition that characterizes Earth and other rocky planets in our solar system. Spectroscopic observations and density measurements indicate that the planet likely contains a substantial proportion of carbon compounds, leading to the fascinating possibility that its interior might contain vast reservoirs of diamond formed under the extreme pressures found deep within the planet. This carbon-rich composition distinguishes 55 Cancri E from most other known planets and suggests that it formed in a protoplanetary disk with a different chemical composition than the one that gave rise to our solar system. The existence of such a carbon world challenges our Earth-centric assumptions about planetary composition and suggests that the building blocks of planets can vary dramatically from one system to another, creating worlds with fundamentally different chemistries and structures. The potential for diamond layers within 55 Cancri E represents one of the most exotic possibilities raised by studies of this remarkable world, as the extreme pressures in the planet's interior could transform carbon into crystalline diamond structures that do not naturally occur on Earth. Models based on the planet's measured mass and radius suggest that it might consist of a core rich in iron and nickel, surrounded by a thick layer of diamond, with a surface potentially covered in graphite or other carbon compounds, rather than the silicate rocks that dominate Earth's crust. Under the immense pressures found within 55 Cancri E, carbon would be subjected to conditions far exceeding those in Earth's interior, potentially creating diamond layers that extend for thousands of kilometers and comprise a significant fraction of the planet's total mass. This scenario, while speculative, highlights the remarkable diversity of planetary compositions that might exist throughout the galaxy and challenges us to expand our understanding of what constitutes a terrestrial planet. The atmosphere of 55 Cancri E represents another area of intense scientific interest, as the planet's extreme conditions create a gaseous envelope quite different from any in our solar system. Observations using the Spitzer Space Telescope have suggested the presence of an atmosphere containing hydrogen, helium, and potentially hydrogen cyanide, a compound that is toxic to life on Earth but might be stable under the extreme conditions found on this world. The planet's atmosphere is likely subject to intense stellar radiation and powerful winds driven by the extreme temperature differences between the day and night sides, creating dynamic circulation patterns that distribute heat throughout the planet. The study of this exotic atmosphere provides valuable insights into how planetary atmospheres behave under conditions far more extreme than those found in our solar system, helping scientists refine their models of atmospheric physics and chemistry. The formation history of 55 Cancri E presents a fascinating puzzle for planetary scientists, as the planet's current close orbit and unusual composition suggest a complex evolutionary path that likely involved significant migration after its initial formation. Current theories propose that 55 Cancri E may have formed farther from its host star in a region where carbon-rich materials were more abundant, then migrated inward to its current position through interactions with the protoplanetary disk or gravitational encounters with other planets in the system. This migration scenario is supported by the presence of 4 other planets in the 55 Cancri system, with a wide range of orbital distances and masses, suggesting a complex, dynamical history that dramatically reshaped the system's architecture. Understanding the formation and evolution of 55 Cancri E provides valuable insights into the processes that can transform planetary systems over time, creating the diverse configurations we observe throughout the galaxy. The study of 55 Cancri E has significant implications for our understanding of planetary diversity and the various forms planets can take throughout the cosmos, demonstrating that the universe can produce worlds with compositions and environments far beyond what we might have imagined based solely on our solar system. This remarkable super-Earth has expanded our conception of what constitutes a terrestrial planet, showing that rocky worlds can have compositions dominated by elements other than the oxygen and silicates that characterize Earth and similar planets. The existence of such exotic worlds challenges scientists to develop more comprehensive models of planet formation that can account for the full range of planetary compositions and structures observed in our galaxy. Each new discovery about 55 Cancri E adds to our growing understanding of the remarkable diversity of planets that exist throughout the cosmos, bringing us closer to answering fundamental questions about how planetary systems form and evolve. The methods used to detect and characterize 55 Cancri E represent the cutting edge of astronomical observation and analysis, showcasing the remarkable precision achievable with modern telescopes and data analysis techniques. The planet was initially detected using the radial velocity method, which measures the subtle wobble of a star caused by the gravitational pull of an orbiting planet, revealing its presence and providing information about its mass and orbital characteristics. Subsequent observations using the transit method, which detects the slight dimming of starlight as a planet passes in front of its host star, allowed astronomers to determine the planet's radius and calculate its density, providing crucial constraints on its composition. More recently, observations with the Spitzer Space Telescope have provided insights into the planet's atmosphere and temperature distribution, demonstrating how multiple observational techniques can be combined to create a more comprehensive picture of distant worlds. The extreme conditions on 55 Cancri E make it an excellent laboratory for studying the behavior of materials and planetary processes under environments far more extreme than any found in our solar system. The planet's surface temperatures are hot enough to vaporize rocks, potentially creating a thin atmosphere of silicate vapors that condense into droplets of lava rain on the cooler night side. This exotic weather pattern represents just one of the many unusual phenomena that might occur on 55 Cancri E, challenging our understanding of atmospheric dynamics and the cycling of materials on planetary surfaces. The study of these extreme processes not only advances our knowledge of this specific world, but also provides insights into the fundamental physical and chemical principles that govern planetary behavior under a wide range of conditions, helping scientists refine their models of planetary science. The public fascination with 55 Cancri E reflects humanity's enduring curiosity about the diverse worlds that exist throughout the cosmos and the remarkable variety of forms planets can take. Since its discovery, this exotic world has captured the popular imagination, inspiring countless artistic renderings and speculative descriptions of what conditions might be like on its surface. These depictions often feature landscapes of diamond mountains, rivers of molten metal, and skies filled with unusual clouds composed of vaporized rock, highlighting the planet's status as one of the most alien worlds yet discovered. While these artistic interpretations remain speculative, they reflect the profound impact that discoveries like 55 Cancri E have on our collective consciousness, challenging us to expand our conception of what constitutes a planet and encouraging us to contemplate the remarkable diversity of worlds that exist throughout our galaxy. The significance of 55 Can 51e in the broader context of exoplanet research extends beyond its exotic characteristics, as it represents an important step in our journey to understand the full spectrum of planetary diversity that exists throughout the galaxy. This remarkable super-Earth has demonstrated that planets can form with compositions and in environments radically different from what we find in our solar system, challenging scientists to develop more comprehensive theories of planet formation and evolution that can account for this diversity. The study of 55 Cancri E has also provided valuable insights into the processes that can transform planetary systems over time, including planetary migration and atmospheric evolution, helping us understand how the diverse configurations of exoplanetary systems we observe today came to be. Each new discovery about this extraordinary world adds to our growing understanding of the complex and varied nature of planets throughout the cosmos, bringing us closer to answering fundamental questions about how planetary systems form and evolve. The future study of 55 Cancri E promises to yield even more insights into this remarkable world and the extreme conditions that characterize it, as upcoming telescopes and instruments offer the potential to refine our understanding of its composition, atmosphere, and surface conditions. Next-generation space-based observatories like the James Webb Space Telescope will be capable of obtaining more detailed spectra of the planet's atmosphere, potentially revealing additional molecular components and providing better constraints on its temperature distribution and atmospheric dynamics. Ground-based, extremely large telescopes currently under construction may eventually be able to directly image 55 Cancri E and other close-in exoplanets, providing unprecedented views of these exotic worlds and potentially revealing surface features that could offer clues about their geological activity and composition. Each technological advancement brings us closer to answering fundamental questions about this remarkable world and the extreme environments it represents, further expanding our understanding of planetary diversity in the cosmos. As we continue to study 55 Cancri E and other exotic exoplanets, each new discovery adds to our understanding of the remarkable diversity of worlds that exist throughout the galaxy, challenging our assumptions and expanding our conception of what constitutes a planet. The existence of a world like 55 Cancri E, with its potential diamond interior, extreme temperatures, and exotic atmospheric composition, demonstrates that the universe can produce planetary configurations far beyond what we might have imagined based solely on our solar system. This expanded view of planetary diversity has profound implications for our understanding of planet formation and evolution, suggesting that the processes that create worlds are more complex and varied than previously thought. The ongoing exploration of 55 Cancri E and similar exotic worlds represents one of the most exciting frontiers in planetary science, offering insights into the fundamental principles that govern planetary systems and the remarkable variety of forms they can take throughout the cosmos.